Okay, let's dive right into this. Have you ever wondered what the universe actually looks like when you zoom all the way down? We're talking way down, to the atomic scale, the literal building blocks of everything around us. Today, we're putting on our detective hats for this explainer because we're unraveling one of the absolute greatest mysteries in modern physics, atomic mechanics. To set the stage for this mystery, just listen to these words from the legendary physicist Richard Feynman. He said, "Things on a very small scale behave like nothing that you have any direct experience about. They behave like nothing you have ever seen." Just think about that for a second. We are about to enter a completely alien world where our classical intuition, that normal everyday common sense that helps us navigate our lives, just completely fails us. So, part one, establishing the baseline, the normal rules of reality. All right, like any good detective, we need to test our macro world suspects before we investigate the really bizarre quantum stuff. Imagine an experiment where we're firing indestructible bullets from a, well, kind of erratic machine gun at an armor plate wall. And this wall has two holes in it. Right behind that wall is a detector, let's say a box of sand, to catch whatever makes it through. So when we fire this gun, how do the bullets arrive? Well, they arrive in distinct individual lumps, right? There are no half bullets, just sharp, solid thuds in the sand, one complete bullet at a time. And the math for this everyday behavior is beautifully simple. If we want to figure out the total chance of a bullet arriving at a certain spot when both holes are open, let's call that P12. It's just the sum of the probabilities for each hole open alone, P1 plus P2. The probabilities simply add up perfectly. You close one hole, you just get the bullets from the other. It makes perfect logical sense, right? Now, let's move on to our second suspect, water waves. Here, instead of a gun, imagine jiggling a wave source up and down in a shallow pool of water toward a similar wall with two holes. Notice how completely different this looks compared to the bullets. Unlike those distinct lumps, the intensity of a wave isn't lumpy at all. It's totally continuous. A wave can have any height and carry any intensity. And this brilliantly illustrates an absolutely crucial physical concept known as interference. When the waves pass through those two holes, they spread out and they overlap. Where the wave peaks add together, you get this massive, high intensity. We call that constructive interference. But where a peak meets a trough, they cancel each other out entirely, leaving flat water. That's destructive interference. The end result is this very distinct wavy pattern of high and low intensities hitting our detector at the back. So let's quickly summarize our two everyday suspects before things get, well, really weird. Particles, like our bullets, arrive in discrete, identical lumps, and their probabilities simply add together. Waves, on the other hand, have a continuous intensity and they actively interfere with each other, creating a pattern of peaks and valleys. This is our baseline reality, two completely distinct, mutually exclusive sets of rules. Which brings us to part two, the prime suspect, the electron anomaly. Okay, time to scale down to the atomic level. This is where we finally meet the prime suspect in our quantum mystery, the electron. Imagine our detector is now an incredibly sensitive Geiger counter, spitting out erratic, distinct clicks as it detects incoming hits. Let me ask you this. What do you actually expect to happen when we fire these electrons? Do they act like the lumpy bullets or the overlapping water waves? Take a look at the resulting curve. That is the actual distribution of electrons hitting the backstop when both holes are open. Look at those wiggles. This right here is the ultimate quantum contradiction. The electrons arrive at the detector in identical, distinct lumps, producing sharp individual clicks one by one, literally exactly like our machine gun bullets. But when you plot where all those individual lumps end up over time, they distribute themselves in an interfering wave, exactly like the water waves. And crucially, the total probability with both holes open is not equal to the sum of each hole alone. It's absolutely baffling. They arrive as individual particles, but somehow they distribute as an interfering wave. Now, at this pivotal point in our detective story, you might literally be shouting the obvious common sense solution at the screen. You're probably thinking, well, let's just watch them. Let's literally look at which hole each electron goes through to see how it's pulling off this impossible trick. And you know what? That is exactly what physicists try to do next. So, we set a trap. We place a really strong light source right behind the wall, directly between the two holes. Because electric charges scatter light, whenever an electron passes through hole 1 or hole 2, it'll scatter a photon to our eyes and we'll see a distinct flash of light. Boom! We will definitively catch the electron in the act of choosing its path. But here is the sheer, mind-bending twist. The very moment we turn on that light and observe which hole the electrons go through, the wavy interference pattern completely disappears. Look at the results. When we watch them, they immediately stop acting like waves and behave exactly like classical bullets again, giving us a smooth, non-interfering probability curve. Turn off the light, the wavy pattern magically returns. The mere act of watching the electron literally changes its behavior. Of course, scientists tried to outsmart the electron. They figured, hey, maybe our extremely bright light is physically jolting the electrons and ruining that delicate wave pattern. Let's use a dimmer light. But remember, light is lumpy too. It's made of individual photons. So a dimmer light just means fewer photons, which means some electrons just slip by entirely unwatched. And guess what? The ones that slip by unwatched make the wave pattern, while the watched ones act like bullets. Then they tried using redder light with longer, gentler wavelengths to reduce the jolt. But longer wavelengths mean lower resolution. We just get these big, fuzzy flashes, and we can't even tell which hole the electron went through anymore. The undeniable result? You absolutely cannot watch the electron without actively disturbing the interference pattern. No way around it. Which leads us to part 3, the resolution. Heisenberg's uncertainty principle. This mind-bending contradiction couldn't just be explained away as some technical glitch in the equipment. It required a profound, complete revolution in how we understand reality itself, formulated in the 1920s as Heisenberg's uncertainty principle. Werner Heisenberg came up with this brilliant thought experiment to bypass the light entirely. He thought, what if we don't shine a light at all? What if we mount the wall itself on tiny, frictionless rollers? If an electron goes through hole 1 and deflects downward to hit the detector, it must push the wall up in recoil. If it goes through hole 2 and deflects upward, it pushes the wall down. By precisely measuring the physical recoil momentum of the wall, we could deduce the electron's path without ever shining a destructive light on it. But here is where the uncertainty principle strikes back with a vengeance. To measure the wall's momentum accurately enough to know which hole the electron used, you have to sacrifice accuracy about the wall's exact position. You simply can't know both perfectly. And if you don't know exactly where the wall is, you don't know exactly where the holes are. That positional uncertainty randomly shifts the center of our interference pattern for every single electron, totally smearing out the wiggles into a smooth classical curve anyway. Any apparatus capable of finding out which path is taken is fundamentally guaranteed to destroy the wave pattern. So the crucial point here is perfectly captured in this realization. Physics has formally given up on the problem of trying to predict exactly what will happen in a definite circumstance. The only thing that can be predicted is the probability of different events. This isn't a failure of our tools, guys. This is a fundamental, inescapable characteristic of nature. The universe at its base level simply does not run on classical clockwork determinism. Now, before we wrap up this explainer, let's clear up one lingering mystery from the very beginning. If all matter has this wave-like probability nature, why didn't we see a wavy interference pattern with our machine gun bullets earlier? Well, it turns out bullets actually do have quantum wiggles too. But because a bullet is so incredibly massive compared to an electron, its quantum wavelengths are impossibly, unimaginably tiny. Our macro-scale detectors and our human eyes just straddle millions of these wiggles all at once, so we only ever see the smooth, average classical curve. Which leaves us with a truly profound thought to end on. If physics has given up on predicting exactly what will happen in a definite circumstance, what does that actually mean for our everyday understanding of reality? Are we just riding on top of a fundamentally unpredictable, probability-driven universe? Let that simmer. Thank you for exploring this fascinating quantum explainer with me today. Keep asking big questions and always keep looking closely at the world around you.
Hey everyone, welcome. Today, we're taking a really mind-bending journey. We are going to start way out in the abstract world of quantum physics and bring it all the way down to the actual, everyday reality you and I are experiencing right this second. We're going to completely rethink how we view the basic building blocks of our universe.
To get us started, let me ask you something kind of wild. Why don't you fall right through the floor? Think about it. Right now, you're sitting in a chair or maybe standing on the ground. Gravity is constantly pulling you down, right? And we know from basic science that atoms are, well, they're mostly just empty space. So what exactly is holding you up? I promise you, by the end of this explainer, you're going to see that the bizarre, almost magical rules of quantum mechanics hold the actual physical answer to that question. So here's our roadmap for today. We're going to hit the wave-particle paradox, the uncertainty principle, see how particles act like waves, figure out why matter is actually solid, touch on quantum energy levels, and finally, look at the limits of predictability. Let's jump right in.
Okay, part 1, the wave-particle paradox, or as I like to think of it, completely rethinking reality.
So if you were taught that waves and particles are two totally separate things, you kind of got to throw that out. It's just an incomplete approximation, and it falls apart when we look really closely at reality. Take what we call a wave packet. When we kind of sorely know where a particle is, its probability forms this wave train. It actually has a finite length. And because that wave train literally has a start and an end, it's mathematically impossible to define a single, perfect, unique wavelength for it. You just can't count the waves precisely. It can't be done.
And okay, why does that matter? Well, in the quantum world, a particle's momentum is deeply intrinsically tied to its wavelength. So if your wave train has an indefinite wavelength, because it's squeezed into a finite little space, then the particle itself fundamentally has indefinite momentum. This isn't just because our measuring tools are clunky or anything like that. No, it's a core property of waves themselves. The whole idea of a particle having a perfectly known location and a perfectly known momentum, yeah, physically impossible.
Which brings us perfectly to section 2, the uncertainty principle. Basically, the ultimate cost of knowing.
Picture this classic setup. You've got particles shooting horizontally from way out in the distance towards a wall, and that wall has a tiny, narrow slit in it. Since they're moving straight horizontally, their vertical momentum is basically zero. But the moment one of those particles squeezes through that slit, boom, suddenly we know its vertical position really well. I mean, it's right there in the gap. We have force to measurement.
But here's the thing. Nature always charges a toll for that kind of knowledge. Classically, you'd expect the particle to just keep flying straight, right? But the quantum reality is radically different. Just by defining that vertical position as it passes through the slit, its probability wave actually diffracts. It spreads out. The vertical momentum suddenly becomes totally unpredictable. And get this, the narrower you make that slit to try and pinpoint its exact position, the wider the particles scatter on the other side. Literally, gaining knowledge about one property completely destroys your knowledge of the other.
All right, part 3, particles acting like waves. Let's look at some tangible proof.
You might already know that when an X-ray hits a crystal, it scatters off these parallel atomic planes inside. It creates this very familiar wave diffraction, where the waves either cancel each other out or amplify each other, all depending on their phase.
But what if you fire solid particles into that same lattice? Things like neutrons or electrons. They do the exact same thing. Seriously, they enter the lattice, bounce off those adjacent atomic planes, and if the wavelengths line up just right, they create a perfect, coherent reflection. You literally have a solid particle acting exactly like a ray of light.
And you can see this brilliantly in a practical application. Let's say you take a long block of graphite, which has a really specific crystal structure inside, and you just blast a chaotic mess of neutrons into it. That graphite essentially acts like a giant wave filter. It scatters almost all of the neutrons right out the sides. But if you look at the measurements, you'll see that neutrons with incredibly long wavelengths just slip straight through those crystal planes without bouncing at all. We are physically filtering solid chunks of matter based entirely on their wave properties.
Okay, section 4. This is the big payoff. Why matter is actually solid, or what we can call the quantum floor.
So, circling back to that fundamental question, how big is an atom? Let's look at a simple hydrogen atom. Under classical physics, that negative electron should just rapidly bleed off its energy, spiral right into the positive nucleus, and just shrink into nothingness. Classical physics literally cannot explain why atoms take up any space whatsoever.
The real answer is something called the quantum compromise. Sure, the electron desperately wants to get closer to the nucleus to lower its potential energy. But remember our good friend the uncertainty principle? If you shrink that atom down, you're confining the electron to a much smaller space. You're pinpointing its location more accurately. And nature's price for that? A massive, totally unpredictable spike in the electron's momentum, which means a massive spike in its kinetic energy.
So the atom is forced into this cosmic tug-of-war. It has to find the absolute perfect balancing point between the electrical pole trying to crush it and that quantum kinetic energy trying to explode it outward. And when we do the math to find that exact point of minimum total energy, we land precisely on 0.529 angstroms, the Bohr radius. The abstract math of wave-particle uncertainty literally predicts the physical measurable size of atoms flawlessly.
And it doesn't just predict the size, it nails the energy too. At that perfect balancing point, the total energy of the electron sits at negative 13.6 electron volts. That's the Rydberg energy. The negative part just means the electron is trapped. It's bound to the atom, meaning you need precisely 13.6 electron volts of energy to pry that electron away and ionize the hydrogen. The math matches reality perfectly. Which finally brings us right back to our hook. When you stand on the floor, the atoms in your shoes are pushing against the atoms in the floor. To compress them, you'd have to squeeze all those electrons into a tighter space. But quantum mechanics flat out says, nope, confining them spikes their momentum, and that requires an absurd massive amount of energy. So the floor isn't holding you up just because it's a dense block of stuff. It's holding you up because those electrons mathematically refuse to have their positions pinned down without putting up an extreme fight. That quantum resistance, that is literally what you feel as physical solidity. How amazing is that?
Moving on to Section 5, Quantum Energy Levels, or as we can think of them, the organ pipes of nature.
Okay, imagine an organ pipe. The sound waves trapped inside can only vibrate at very specific, resonant frequencies, right? Well, atoms are kind of the same. The probability waves of electrons trapped inside an atom can only exist at specific, allowed energy states. They can't just hang out anywhere they want. An electron might sit at the ground state, or jump up to step 1 or step 2, but it absolutely cannot hover in the empty space between them. And when an electron drops back down from a higher state to a lower one, it spits out that extra energy as a tiny photon of light. Because these energy levels are exact, fixed steps, the light that comes out is always at highly specific, predictable frequencies. This is called the Ritz combination principle. When scientists look at the light from glowing gases or distant stars, they see these exact same distinct frequencies. It's absolute, undeniable proof that nature really does operate on this quantum model of distinct steps. All right, our final section, number 6, the limits of predictability, chance versus determinism.
You'll often hear people say that quantum mechanics totally destroyed the idea of a predictable, deterministic universe because it's all based on probability. But honestly, that's kind of a myth. Even in classical physics, think about a waterfall. Technically, if you knew the exact position of every single particle of water, you could predict where every drop would land. But practically, the tiniest, unmeasurable error multiplies so fast that the waterfall acts completely randomly. Classical physics was already deeply, practically chaotic. Quantum mechanics just updates this. It tells us it's not just practically impossible to know the exact future, it's fundamentally impossible. At its core, the universe just runs on probabilities. So I want to leave you with this lingering thought, one inspired by Richard Feynman. A lot of folks like to use quantum randomness to explain human free will, They say, we have free will because our atoms are unpredictable. But wait, if classical physics was already practically unpredictable because of pure chaos, wouldn't a completely classical brain still feel exactly like it had free will? Are your choices truly these quantum leaps of probability? Or are they just the beautiful, chaotic unfolding of countless, incredibly complex classical interactions? It really completely changes how you view your own mind, doesn't it? Thank you so much for exploring the quantum realm with me today.
Welcome to this explainer. Today, we're leaving everyday classical physics totally in the dust. We aren't going to talk about how air moves in a sound wave or how light bends through a lens. Nope. Instead, we are jumping straight into the advanced, mind-bending world of quantum mechanics. And believe it or not, this stuff relies on some of the simplest math you can imagine. We're talking about probability amplitudes, a concept that absolutely shatters our everyday intuitive understanding of the world.
So, let's dive into this incredibly bizarre question. How does nature actually know if you're watching it? In this explainer, we're going to act as quantum detectives. We'll investigate a series of strange quantum crime scenes to uncover exactly how the universe decides to behave. And our ultimate clue, the one thread that ties all these mysteries together, is a little concept called distinguishability.
All right, Chapter 1, the quantum jump and the rules.
Before we can start examining our quantum crime scenes, we need our primary detective tool, and that is the probability amplitude. Now, don't let the technical term intimidate you. It's essentially just a mathematical tool, a complex number with a magnitude and a direction. And when you take the absolute square of this number, it gives you the actual real-world probability of a particle arriving at a specific state or location. You can kind of think of the amplitude as this invisible, wave-like mechanism operating totally behind the scenes, dictating exactly where particles like electrons or neutrons are eventually going to end up.
And this brilliantly illustrates the two fundamental rules of our quantum detective work. First up, if a particle takes steps in succession, meaning, it goes from point A to point B and then from point B to point C, you multiply the amplitudes of those steps. Second, if a particle has alternative routes to reach its final destination, meaning it could take path A or path B, you add the amplitudes together. It's really that simple. You multiply for succession and you add for alternatives.
Moving on to Chapter 2, the two-slit mystery.
Let's apply our new rules to the absolute most famous mystery in physics, the two-slit experiment. Imagine we have a source of electrons, a wall with two small slits, and a detector screen at the back. When electrons pass through this wall, they end up forming this wavy interference pattern on the detector. But why? Well, because we physically do not know which slit any given electron went through. They are indistinguishable alternative routes. So, following our rule, we must add the amplitudes for hole 1 and hole 2 together, which creates that beautiful wave-like interference pattern of probabilities.
Now, let's see how this builds when things get a bit messy. Even with a much more complicated setup, like, say, adding a whole second wall with 3 holes, A, B, and C, the math doesn't actually get any harder. We just act as methodical detectives. We map out all the possible alternative routes, say hole 1 to hole A to the detector, or maybe hole 2 to hole C to the detector. We multiply the amplitudes for each successive step of a single route, and then we just add all those different route amplitudes together. The total interference is just the sum of the whole shebang.
But here is where the mystery really deepens. What happens if we try to outsmart nature? What if we place a light source right behind the slits, along with some photon detectors, to physically watch and record exactly which slit each electron goes through? By doing this, we are actively trying to distinguish the path.
If our detectors perfectly catch which slit the electron used, an absolutely incredible thing happens. That wavy interference pattern, it completely vanishes. Poof! It flattens out into a smooth curve. The interference is just gone. You see, if we can tell the difference between the routes, if those final states are distinct, we have to add the final independent probabilities, not the amplitudes. By making the routes distinguishable, we literally change the final reality of where the electrons landed.
And you absolutely cannot cheat the system here. As the brilliant physicist Richard Feynman pointed out, nature does not know what you are looking at, and she behaves the way she is going to behave whether you bother to take down the data or not. You can't trick nature by setting up the detectors, capturing the light, but then just ignoring the data later. The universe doesn't care if you actually read the data. If the event creates a distinguishable final state in the physical world, the routes do not interfere. Period.
Okay, Chapter 3, the neutron spin secret.
Let's escalate the weirdness a bit and head to our second crime scene. Picture this. We shoot a beam of low-energy neutrons at a crystal lattice to see where they bounce into our counter. Because they're low energy, the neutrons bounce off the atomic nuclei without knocking the atoms out of place. The crystal stays perfectly intact. Now, if the nuclei in that crystal have 0 spin, we get massive, sharp interference peaks. Since the crystal is completely unchanged, we have no idea which atom the neutron actually bounced off of. The routes are indistinguishable, so the amplitudes interfere perfectly. But if the nuclei do have spin, we suddenly get this mysterious, smeared-out background alongside the peaks. So what's going on? Where is this smooth, non-interfering background coming from?
Well, it all comes down to a hidden record. Neutrons have a spin of 1/2. So the absolutely crucial point here is this spin-flip rule. If a neutron with spin up hits a nucleus with spin down, they can actually exchange spins during the bounce. The neutron flips down, the nucleus flips up. And by flipping that specific nucleus's spin, the neutron has left a physical record in the crystal of exactly which atom it hit. It's like leaving a fingerprint. Because that route is now physically distinguishable from all the others, it no longer interferes. We add probabilities, not amplitudes, which results in that smooth, smeared-out background.
All right, let's look at Chapter 4, the identical particle twist.
Now for the ultimate mind bender. What happens when particles crash into identical twins of themselves, when there are no labels whatsoever? Let's start with a normal collision. We smash an alpha particle into an oxygen nucleus. We have a detector set up. If something hits the detector, we can easily tell if it's the alpha particle or the oxygen nucleus because they are physically different particles. They are clearly distinguishable. So we simply calculate the probability of the alpha particle arriving, calculate the probability of the oxygen arriving, and we just add those probabilities together. Easy.
But watch what happens if we change the target. What if we smash alpha particles into a target made of identical alpha particles? When a particle hits our detector now, we physically cannot tell if the detector caught the incoming bombarding bullet or if it caught the recoiling target particle.
They are perfectly identical helium nuclei. There's literally no way to know.
And because these two specific routes, detecting the bullet versus detecting the target, are completely indistinguishable, the rules of the universe dictate we must add their amplitudes. When you run the math on this interference at a 90-degree scattering angle, the result is exactly twice as much scattering as classical physics predicts. No way, right? The sheer fact that the particles are identical literally doubles the physical outcome.
And if you think that's strange, identical electrons have a uniquely bizarre rule. When identical electrons exchange roles, their amplitudes actually interfere with a negative sign, meaning they literally cancel each other out. If two colliding electrons have parallel spins, say they're both pointing up, we can't tell them apart, but their amplitudes subtract from one another. However, if they have antiparallel spins, one up, one down, we can easily distinguish them by checking the spin at the detector, which means they don't interfere at all.
So, if we use unpolarized beams of electrons, just a completely random mix of spins, we as detectives have to map out every single distinguishable possibility. We check the up-up collisions, where they interfere negatively. We check the down-down collisions, and we check the up-down collisions where they don't interfere at all. We calculate the separate probability for every single distinguishable scenario, and only then do we sum those separate probabilities together to get the final overall scattering rate.
Our quantum detective work has revealed nature's ultimate unbending rule. Distinguishability dictates reality. If a process leaves a physical record, if there is any way in principle to tell the difference between two paths, the universe calculates reality using independent probabilities. But if the paths are truly indistinguishable, the universe calculates reality using interfering amplitudes.
We want to leave you with this final, staggering thought. This whole thing isn't about human consciousness or someone in a lab coat looking through a microscope. It's fundamentally about physical information. If the mere existence of a hidden record or the absolute identical nature of two particles physically alters the distribution of matter, what does that mean for how deeply observation and information are woven into the very fabric of nature itself? Keep that in mind next time you think you're just a passive observer in this universe. Thanks so much for joining us on this explainer.
Welcome to this explainer. Okay, today we are diving into something absolutely wild. We're setting the stage for a mind-bending exploration into the invisible, microscopic rules that literally build our physical universe. We're going to unpack some pretty profound concepts from physics, and honestly, by the end of this journey, you're going to see the solid objects around you in an entirely new light.
So here's a question for you. Why doesn't the matter in your body just collapse into a tiny dot? Seriously, think about it. It's a heavy question. We know that atoms are, well, mostly empty space, right? And gravity and electromagnetism are basically pulling things together all the time. So why do you take up space? Why don't you just fall straight through the floor? The answer actually lies deep in the quirky, almost magical behavior of subatomic particles.
Section 1. The Quantum Identity Crisis.
To answer that question about why you don't just shrink into a dot, we really have to start by wrapping our heads around a super strange reality of the quantum realm. When we talk about identical particles in quantum mechanics, like two electrons or two photons, we don't just mean they look similar. We mean they can in no way be distinguished from one another. Like, if you swap two identical particles, the universe itself literally cannot tell that anything has changed. Because we can't tell them apart, even in principle, this fascinating mathematical quirk happens. Their probabilities actually interfere with each other when they interact or scatter. They're not like independent billiard balls bouncing around. Their destinies are completely mathematically tangled.
And here's where it gets interesting. Nature divides all these identical particles into two fundamentally opposed camps. First up, we have Bose particles, or bosons. Think of photons of light or mesons. When these particles interact, their quantum amplitudes actually add together. They're highly sociable, they love a crowd. Then, on the flip side, we have Fermi particles, or fermions. Think electrons, protons, and neutrons. When fermions interact, their amplitudes subtract. They are fierce, antisocial loners. This grand duality, it's literally the foundation of everything. Section 2. Bose particles, the crowd. Let's focus entirely on that first group for a minute, the highly sociable Bose particles. The secret to this sociability comes down to a simple little math multiplier, n plus 1. Basically, if you have n Bose particles already occupying a certain state, let's say they're moving in a specific direction with a specific energy, the probability of one more identical Bose particle joining them doesn't just stay the same. It gets multiplied by n plus 1. In other words, if there are already photons in a state, the chance of getting a new photon into that exact same state gets a massive boost. The presence of the crowd actively attracts more particles to join in.
They're pretty much the ultimate quantum copycats. Section 3. Superfluids and light.
Now, this microscopic copycat math might seem a bit abstract, but it scales up to create some of the absolute most spectacular macroscopic phenomena we see in the universe. Take lasers, for example. A laser is essentially just a massive number of photons perfectly forced into the exact same state, all moving together. Then there's blackbody radiation, which is how we understand the frequency spectrum of a hot glowing object, and that completely relies on photons acting as Bose particles. And get this, superfluid liquid helium. At incredibly low temperatures, helium-4 atoms, which behave as Bose particles, suddenly all drop into the exact same quantum state. Because they're moving as one single rigid unit, the liquid flows with absolute zero friction or viscous resistance. It'll literally crawl up and over the sides of a glass. Unbelievable, right?
Section 4. Fermi particles, the loners. Okay, so now we pivot sharply to the opposite team, the Fermi particles. And remember, these are the particles that actually make up you and me. The absolutely crucial rule here is the Pauli exclusion principle. Because the amplitudes of Fermi particles subtract instead of add, the probability of two electrons perfectly sharing the exact same state, meaning the same position, same momentum, and same spin, drops to absolute zero. It's just fundamentally impossible. Fermi particles absolutely refuse to share. If one electron is in a state, the door is closed, locked, and bolted for any other electron trying to enter that identical state.
Just imagine a hypothetical universe for a second, where electrons were sociable Bose particles. If electrons like to crowd together, every single electron in an atom would just plummet straight down to the lowest energy state, piling on top of each other right next to the nucleus in one dense spherical cloud. A helium atom, a lithium atom, a heavy lead atom, they would all look basically exactly the same, just denser and denser little round balls. In this hypothetical universe, complex chemistry simply couldn't exist. There's no way.
But thankfully, in the real universe, electrons are antisocial Fermi particles. Once that lowest level near the nucleus is full, the next electron has to take up a completely different state, further out from the nucleus. This forces electrons to spread out into distinct, complex geometric shells. And because those outer electrons are pushed further away, they're much more loosely bound. This difference in where outer electrons live is exactly what gives different atoms their totally unique chemical properties.
Section 5. Why matter exists.
Let's bring this all the way back to our everyday world, and back to that profound question we asked at the very beginning. If electrons hate sharing so much, how do chemical bonds even form in the first place? Well, there's a loophole. The exclusion principle says no two electrons can have the exact same state, and that includes their spin. An electron can spin in one of two directions. So you actually can put two electrons tightly together between two nuclei to form a strong chemical bond, but, and this is a big but, only if their spins are pointing in perfectly opposite directions. This stubborn little rule is literally the driving engine behind all of molecular biology. And here's another mind-blowing consequence. We just said that if electrons get pushed into the same space, their spins have to be opposite, right? Well, in some crystals, like iron, you have free wandering outer electrons mixing with tightly bound inner electrons. Because the exclusion principle completely prevents them from occupying the same state, it indirectly forces this violent sorting mechanism. The inner electrons are actually forced to align their spins in the exact same parallel direction, just to keep the wandering electrons happy in opposite states. This massive alignment of quantum spins is what creates ferromagnetism. Seriously, every time you stick a magnet to your fridge, you are feeling the literal, physical force of the Pauli exclusion principle. How cool is that?
As the legendary physicist Richard Feynman so profoundly put it, the variety that is represented in the periodic table is basically a consequence of this one rule: chemistry, biology, DNA, the fact that your chair holds your weight and you don't just fall straight through the floor into the center of the Earth. All of this exists purely because the electrons inside your atoms are Fermi particles that flat out refuse to overlap. Their antisocial nature is exactly what gives matter its volume, its structure, and its stability.
So, I want to leave you with this provocative thought to chew on today. What if the rules just flipped tomorrow? What if the universe suddenly decided that electrons were sociable Bose particles and photons were antisocial Fermi particles? Light would refuse to overlap, plunging our lasers into total darkness, while all the matter in your body and the planet around you would lose its structural integrity and just collapse into a dense, featureless smear. It's a terrifying, yet totally fascinating thought, and it all comes down to the delicate, invisible rules of identical particles. Thanks so much for joining me on this explainer, and hey, keep questioning the reality around you.
Welcome to this explainer. Okay, today we're diving straight into the core principles of quantum mechanics. And honestly, the best part? Absolutely no advanced calculus is required. We're going to explore exactly how reality operates down at the smallest possible scales, and we'll be guided by one of the most famous thought experiments in all of physics.
So here's our roadmap for today. First, a new quantum language. Second, the Stern-Gerlach filter. Third, tilted filters and probability. Fourth, the Humpty Dumpty mystery. And finally, the matrix machinery. Let's get right into it.
Section 1. A new quantum language. Stepping away from classical mechanics. Look, to truly grasp what's happening today, we have to completely let go of classical physics. No bouncing balls, no planetary orbits. We are learning a completely new, purely quantum language.
Okay, let's dive into this. Imagine shooting a beam of atoms through a magnet, one with a very specific uneven magnetic field. Now, in classical physics, you'd expect those atoms to just kind of smear out based on how they were randomly spinning, right? Well, that is definitely not what happens. Instead, the beam surprisingly splits vertically into exactly 3 distinct, separate paths. One beam goes up, one goes straight, and one goes down. It's perfectly quantized. Crazy, right?
Because we get exactly 3 beams, we're going to call the atoms in our experiment spin-1 particles. Now, just to be clear, for our purposes, spin-1 doesn't mean it's spinning like a little toy top. It simply means a particle that splits into exactly 3 distinct beams, plus, 0, and minus, when passed through our machine. We're entirely focused on this one bizarre behavior. Moving right along to Section 2, the Stern-Gerlach filter, building the perfect theoretical machine. We're going to take that basic splitting magnet and upgrade it so we can control our atoms perfectly.
To make our perfect filter, we conceptually break it into 3 steps. First, we split the incoming beam into our 3 paths, just like we saw before. Second, we use a longer reverse magnet to bend those paths right back toward the center axis. And third, we use a final magnet to recombine the beams at the exit, ensuring they all leave from the exact same place they started.
Inside this modified setup, we basically have 3 high-gradient magnets. The first one splits the beam, the middle one, which is twice as long, bends them back, and the third recombines them. If an atom goes through completely unimpeded, it takes this sort of invisible detour and pops out the other side almost as if nothing ever happened.
But here is where we really get control. By inserting physical blocks, like little masks, inside the machine, we can literally block certain paths. For instance, if we block the bottom 2 paths, only the atoms on the top plus path actually make it through. We call this a pure state. To keep track of all this, we'll use some handy shorthand. The curly brackets represent the apparatus, and the internal lines show exactly which paths we've blocked off.
So what happens if we challenge them? Let's move to Section 3, tilted filters and probability, changing the angle.
Okay, we've filtered our atoms, so we know with 100% certainty they are in the plus state of our first machine. But here is the big question. What happens to that pure, completely predictable state if we take those exact same atoms and send them into a second machine that's tilted at an angle?
So we have our first machine, let's call it S, producing a pure plus beam. Then those atoms enter a second machine, T, which is tilted at angle alpha. Now, you might think a plus atom from S remains a plus atom in T. I mean, that makes sense, right? But it doesn't. The atom is literally forced to reorient itself into the new tilted states, plus T, 0T, or minus T. It's forced to choose a brand new path based entirely on the new orientation of the magnet.
So the absolutely crucial point here is this entirely new set of rules for reality. When the atom enters the tilted machine, it reorients entirely by luck, or, well, pure probability. There's a specific mathematical chance it takes the top, middle, or bottom path. Furthermore, once it's filtered by this new tilt, it develops temporary amnesia. Seriously, it completely forgets it was ever a plus S atom. Its future depends only on its current base state. And of course, the probability of it entering one of those 3 new paths must sum up to exactly 100%, because, it has to go somewhere.
Section 4, the Humpty Dumpty mystery, the climax of quantum interference. Everything we've built so far is leading us right to this deep, mind-bending phenomenon. Now, what's really interesting here is an absolute paradox. Imagine sending a beam through our S filter, then a tilted T filter with 2 paths blocked, and finally another S filter. A certain fraction of those atoms will successfully make it all the way to the end. But if you reach into that middle T filter and open all the paths, literally removing the obstacles, suddenly 0 atoms make it through to that final state. Let me repeat that, because it's wild. By making it easier to pass, fewer atoms get through. Actually, scratch that.
None do. No way, right?
So how on earth is this possible? Well, as physicist Richard Feynman brilliantly explains, when the middle filter is wide open, the beam is split and flawlessly recombined. Humpty Dumpty has been put back together again. Because all three paths are open, the quantum amplitudes of the particle taking those paths perfectly interfere with one another. It's exactly like ripples on a pond canceling each other out. The result? The atoms exit the wide-open middle filter completely unchanged, retaining perfectly their original plus S state. They completely ignore the tilted machine because they were never forced to pick just one path.
To really resolve this mystery, we have to look under the hood. Section 5. The matrix machinery, calculating the odds.
This right here is the true engine of quantum mechanics. Where classical physics uses forces and masses, quantum mechanics uses a matrix of amplitudes. Because there are 3 starting states in our first machine and 3 ending states in our tilted machine, there are 9 possible paths. We get a 3x3 matrix representing the 9 complex amplitudes that completely describe any apparatus. If you know these numbers, you simply multiply the probabilities, account for the interference, and boom, you can mathematically predict exactly what the atoms are going to do.
And the best part? This applies perfectly to the real world too. If atoms come directly from a hot furnace, they haven't been neatly sorted by our first filter yet. They're unpolarized. Quantum mechanically, we handle this by saying the atoms are just a random mixture of probabilities, effectively an even 1/3 split across our 3 base states. We just take our matrix machinery and apply it evenly to this starting mixture to predict our outcomes. It all just seamlessly clicks into place.
So, the ultimate takeaway here is that quantum mechanics isn't magic. It might feel completely counterintuitive that opening a physical path actually stops particles from getting through, but once you abandon classical physics, it makes perfect sense. It's the new mathematical machinery of reality, based entirely on interfering amplitudes and probabilities. Once you know the matrix, you can basically predict the universe.
I want to leave you with this final thought today. If opening more paths in a machine literally allows fewer atoms to get through, what else about our daily macroscopic reality is just an illusion hiding behind the invisible math of interfering amplitudes? Thank you so much for joining this explainer. Keep looking closely at the world around you because for sure, reality is far weirder than it seems.
Okay, we're embarking on a pretty wild journey today. This is a deductive excursion into, honestly, one of the most counterintuitive realms in all of physics, quantum spin. But here's the coolest part. We aren't going to be dragging you through a laundry list of complex experimental data today. No way. Instead, our goal with this explainer is to use pure abstract reasoning, guided entirely by the fundamental symmetries of space itself, to deduce the bizarre mathematical rules of spin 1/2 particles. We're going to see how literally just thinking logically about 3D space can unlock some of the deepest secrets of the quantum world. Here's how we're going to tackle this. First, the quantum spin puzzle. Then we'll look at the rules of the z-axis, followed by the 360-degree paradox. After that, expanding to y and x, and finally, we'll tie it all together with the universal transformation. Let's get into it. All right, part 1, the quantum spin puzzle. So before we look at any actual physical machines, we need to introduce our core mathematical tool. It's called the transformation matrix. Basically, this is just a set of coefficients that relate the probability amplitudes from one base system to another. Think of it kind of like a universal translator, right? It allows us to seamlessly translate the mathematical description of a quantum state from one physical orientation in space into a completely different orientation. Now, let's ground this abstract math in a real physical device. You're looking at the improved Stern-Gerlach apparatus. When a beam of spin 1/2 particles enters from the left side, boom! It splits into 2 distinct paths based on the magnetic field inside. You get an up beam and a down beam, and those are our 2 base states, plus and minus. If we just block the bottom path, we've successfully prepared a pure up state. Seems simple enough, right? But here's where things get a little tricky. What happens if we move the machine? We can define an arbitrary axis in a coordinate system, so if we want to start chaining multiple Stern-Gerlach machines together, we desperately need a way to mathematically describe these different physical orientations. We have to know exactly how the up and down states of the first machine map onto the up and down states of a second machine that might be pointing in a completely different direction. Let's actually picture chaining two of these apparatuses together. We'll call them S and T. If a particle is prepared in a pure up state in apparatus S, and it travels right into a secondary apparatus T, which is oriented at a totally different angle, let's call it alpha, what is the probability that it actually gets through? How do we even begin to calculate the amplitude for going from state S to state T? Well, that is exactly the puzzle we're going to solve right now using pure logic. Moving right along to section 2, rules of the z-axis. Check out these two scenarios. In scenario A, over on the left, our primary apparatus is perfectly in line with our secondary apparatus. But in scenario B, the secondary apparatus is rotated 90 degrees around the z-axis. Now, intuitively, since the magnetic fields are still perfectly parallel in both cases, the up beam from the first machine really should still be the up beam in the second. The absolute probabilities are exactly the same, but look super closely at the path there. In scenario B, the whole system is turned a corner. And you have to ask, does the particle actually know it turned a corner? Because if we chained a third machine to this setup to analyze the x or y directions, the results would change dramatically based on this rotation. So logically, while the magnitudes of the probabilities stay the same when you rotate around the z-axis, there absolutely must be some kind of mathematical phase shift occurring behind the scenes. So the absolutely crucial takeaway here is this. When you rotate the apparatus around the z-axis, the absolute probabilities remain totally equal, but the phases shift continuously with the rotation angle. This phase shift? It's the unseen variable. It's the hidden mechanism that explains why particles behave so weird when we test them further down the line with other apparatuses. It's basically an invisible consequence of just rotating an object in physical space. Which brings us to section 3. And honestly, this is my favorite part of the whole explainer, the 360-degree paradox. I'm going to pose a really basic question to you. What happens if we rotate the entire apparatus by 360 degrees? Just common sense, right? If you turn something completely around 360 degrees, you are right back exactly to your starting state. Nothing should change at all. But get a load of the incredible reality of quantum spin 1/2 particles. If we actually run the math based on those phase shift rules we just figured out, a 360-degree rotation actually multiplies all the amplitudes by -1. Literally, -1. Now, don't panic. The physical reality does remain unchanged, because when you square a negative amplitude to get a real-world probability, it becomes positive again. No harm done in the real world. But mathematically, the quantum state has been totally inverted. To perfectly reproduce the original mathematical state, you actually have to rotate the apparatus 720 degrees. That is 2 full rotations. It's so wildly counterintuitive, but it's a fundamental truth deduced entirely from the logic of spatial rotation. Okay, section 4, expanding to y and x. So let's think about a 180-degree rotation, but this time around the y-axis. If we take our second Stern-Gerlach apparatus and rotate it 180 degrees about y, we are essentially turning the whole machine completely upside down. Logically speaking, what was the up beam for the first machine now just enters the down channel of the second machine. A 180-degree rotation about y simply flips the plus and minus states mathematically. It's a clean swap. All right, so now we need the rules for the x-axis. But here is the brilliant part. Instead of starting from scratch, we can figure them out just by combining our known y-axis and z-axis rotations. To get a rotation around x, we mathematically simulate turning the z-axis down onto x using our y rotation rule, doing our phase shift rotation around this newly positioned z-axis, and then just rotating it back. This is an amazing property of the symmetry of space. Complex rotations can be built directly from simple, known rotations. And that little logical trick leaves us with a perfect synthesis of all the specific directional rules we just deduced. We now have our translation coefficients for rotations around z, x, and y. So if you know the state of a particle in one machine, and you rotate the next machine by any angle around these primary axes, this cheat sheet right here gives you the exact math you need to predict the new probabilities. Finally, section 5, the universal transformation. We can visualize this next step with the incredibly elegant geometry of the Euler-Angles framework. This takes the super abstract concept of arbitrary rotations and brings it right down into a clear 3D space. Basically, any relative orientation of two machines, I don't care how wildly angled or tilted they are relative to one another, can be described purely by 3 sequential angles: alpha, beta, and gamma. By stringing our individual rules together, we just follow a neat little 3-step combo. Step 1, we apply a rotation by beta about our original z-axis. Step 2, we apply a rotation by alpha about our newly positioned x-axis. And finally, step 3, we apply a rotation by gamma about our final z-axis. And because we deduced the math for z and x rotations just a minute ago, we simply multiply those transformation matrices together. The result? You get a universal mathematical formula that lets us calculate the probability amplitudes for a machine pointing in literally any direction.
And I think this highlights the true beauty of what we've achieved today. As noted in the source material for this explainer, whether you're dealing with 3 states or the 2 states of the spin 1/2 particles we've just been looking at, these coefficients can be found purely by abstract reasoning. Just think about what you should take away from this for a second. We didn't measure endless particles in a lab to find these complex transformation matrices. We deduced incredibly deep fundamental properties of physical reality using absolutely nothing but pure logic and the basic symmetries of space.
Which leaves us with a genuinely fascinating final thought. If pure logic and just a basic understanding of spatial geometry can dictate the wildly counterintuitive behavior of quantum spin particles, right down to that bizarre 720-degree paradox, what other mysteries of the universe are out there waiting for us to unravel them, simply by thinking about the symmetries of space? Thank you so much for following along with this highly structured logical explainer. Keep thinking, keep analyzing, and I'll catch you on the next one.
Welcome to the explainer. I gotta tell you, I am absolutely thrilled about what we're diving into today. We are going to completely demystify one of the most mind-bending aspects of reality, how quantum probability actually behaves over time. We're going to strip away all the dense, intimidating math and just trace the journey of a single quantum particle to uncover the beautiful, purely visual logic of quantum amplitudes.
But right off the bat, let's start with the ultimate mystery. Picture this. You've got an alpha particle, and it is locked deep, deep inside a uranium nucleus. Now, according to the strict, unbreakable rules of classical physics, that particle has absolutely zero chance of getting out. It literally doesn't have the energy to climb out of its potential well. It's totally trapped. And yet, it escapes anyway. No way, right? How on earth does a particle break out of an impenetrable trap without the energy to do so? Well, to solve this, we have to look closely at the very fabric of quantum mechanics. Okay, Section 1, Particles at Rest. Think of this whole thing like a detective story. Before we can solve the mystery of our escaping particle, we need to lay down the ground rules of the quantum world. So, let's start as simply as humanly possible, with a particle doing absolutely nothing, just sitting there, perfectly at rest.
You see, in quantum mechanics, a particle isn't just some tiny, hard little dot. It's actually described by what we call a probability amplitude. Now, you can just think of this amplitude as a complex wave. The intensity, or if you want to get technical, the square of this wave, tells us the probability of finding the particle in a given spot. But here is the real secret. Even when a particle is completely at rest, its amplitude is never frozen. It has a phase that is constantly rotating. It's ticking away in time, exactly like an invisible internal clock. And the speed of that ticking? It's driven entirely by the particle's rest energy, which is its mass. So everywhere in space, the amplitude is exactly the same, just ticking, ticking, ticking. This invisible rhythm is literally the foundation of everything around us.
Moving right along to Section 2, Particles in Uniform Motion. Let's actually take this particle on a journey. What happens when this ticking clock of a particle starts to move? Well, to figure that out, we have to connect our quantum clock to Einstein's rules of relativity.
And what's super fascinating here is how we can visually map out that motion. Imagine parallel lines that represent equal phase, basically the synchronized ticking of our resting particle across space and time. But if we shift our perspective to a moving frame, Einstein's rules tell us that space and time get all mixed up. Because time and space are totally intertwined in relativity, the simple time ticking of that resting particle actually translates into a variation across space once it's moving. And that spatial variation? That is exactly what we call the de Broglie wavelength. The wave nature of matter is quite literally just the ticking of a particle's internal clock, just viewed from a moving frame. How cool is that?
All right, Section 3, Crossing Potential Barriers. So we know our particle has a wavelength when it moves. But what if we add another layer of complexity? Let's say our moving particle flies into a region with a completely different potential energy. Maybe it enters a metal box charged with a different voltage.
Imagine our particle is moving along, and it enters a region where the potential energy suddenly drops.
Now, in the classical, everyday world, if a ball rolls down a hill into a lower potential, it speeds up, right? It gains kinetic energy and momentum. Well, in the quantum world, we see that exact same thing translated into waves. As the particle gains momentum, its wavelength physically compresses. The wave literally gets tighter and tighter together.
Which brings us to a massive takeaway, the quantum rule. If the space isn't changing over time, the wave's frequency, meaning how fast it oscillates in time, absolutely must stay perfectly constant across that boundary. Why? Because frequency is just the quantum equivalent of total energy. And since total energy is conserved, the frequency is conserved. But since the potential energy dropped, the kinetic energy, and therefore the momentum and the wavelength, had to shift to make up the difference. This perfectly, beautifully links our everyday classical energy conservation directly to the bizarre behavior of quantum waves.
Now for Section 4, the quantum tunneling effect. We are ready to seriously raise the stakes here. What happens if, instead of dropping into a lower potential, our particle faces a massive, seemingly insurmountable wall of potential energy? A barrier where the required kinetic energy to cross it would technically have to be negative.
Now, classically, if you throw a ball at a wall, it doesn't have the energy to climb. It just bounces straight back, 100% reflection. But quantum mechanics is weirder. As the amplitude approaches and hits the wall, inside that forbidden zone, the amplitude doesn't just instantly vanish. Instead, it turns into a real exponential function, decaying incredibly rapidly. It fades out.
But wait, here comes the ultimate quantum surprise. What if that potential barrier is really, really thin? The exponentially decaying amplitude enters the barrier, fading fast, sure, but it actually reaches the other side before it completely dies out. And the moment it hits the other side, where the potential drops back down, the kinetic energy becomes positive again, and the wave just resumes its normal oscillation. The particle has miraculously tunneled right through a solid wall. No extra energy needed.
And boom, that brings us right back to solving our opening mystery, the alpha particle trapped in the uranium nucleus. When modeling this, there's a massive repulsive potential wall surrounding that deep nuclear well. Inside the nucleus, the wave is just bouncing around like crazy. But at the barrier, the amplitude decays exponentially. However, because the barrier isn't infinitely thick, a tiny, microscopic sliver of that wave actually leaks out the other side. The trap, it turns out, wasn't perfectly sealed after all.
Honestly, it creates a profound sense of awe when you really look at the scale of these numbers. Inside that nucleus, the alpha particle's amplitude is smashing back and forth against the barrier roughly 10 to the 22nd power times every single second. 10 to the 22nd. It is frantically trying to escape. Yet, the barrier is so incredibly thick and the decay is so severe that it takes an average of 4.5 billion years for an alpha particle to actually successfully tunnel out and cause the uranium to decay.
As this quote beautifully lays out, the math behind that decay gives us a factor of e to the power of negative 45. That is an unimaginably, mind-bogglingly small chance of leaking through on any given bounce. But quantum mechanics tells us that tunneling isn't just a possibility, it is absolutely inevitable if you just wait long enough.
Moving on to Section 5, the classical connection. Okay, so we've just seen how incredibly weird and unintuitive quantum mechanics can be with things like tunneling. But let's shift gears for a second. I want to show you how these exact same bizarre quantum rules are actually responsible for the very normal, reliable, classical forces we experience every single day.
Get ready for a major aha moment. Think about standard, everyday Newtonian physics. A particle flies through a force field, like gravity pulling downward, and its path bends. Simple. Now consider the quantum view. We have our probability wave nodes traveling along. But wait, the potential energy is different at the top of the path than it is at the bottom. And we know that because the potential varies, the momentum varies, and therefore the wavelength has to vary. The wavelength literally gets shorter at the bottom than at the top. This causes the entire wave to refract and bend, exactly like a light wave bending when it hits a glass lens. Guys, the classical deflection of a particle is literally just the refraction of quantum probability waves. They are the exact same phenomenon. Mind blown, right?
All right, Section 6, Spin and Magnetic Fields. For the final stage of our particle's journey, we're going to look at something purely quantum, internal spin. We've talked about motion and potential energy, but now let's introduce a magnetic field to see how it messes with a particle's internal magnetic moment.
We can see this perfectly in a real-world muon decay experiment. In this specific setup, polarized muons, which just means their spins are all perfectly aligned in a specific direction, are shot into a block of material where they're brought to a complete stop.
While they're just sitting there, they get subjected to a vertical magnetic field, and eventually, those muons decay into electrons. So here is what the quantum math dictates. When a particle sits in a magnetic field, the field interacts with its magnetic moment. If the particle is in a pure spin-up state, the field interacts with its phase at a certain specific rate. If it's spin down, it changes the phase at the exact same rate, but in the complete opposite direction. Now, because our muon starts out pointing sideways, it's actually an equal 50-50 mixture of spin-up and spin-down amplitudes.
And because those two underlying amplitudes are rotating their phases in totally opposite directions over time, they start to interfere with each other. This creates a beautiful cosine squared curve if you map out the probability of finding the muon spin still pointing in its original direction over time. It starts at 1, smoothly drops all the way to 0, and then oscillates right back up. The muon spin direction is literally precessing. It's sweeping around in a circle like a wobbling top, and it's driven entirely by the ticking interference of its internal quantum amplitudes.
And that brings us to the end of our explainer today. We've seen how absolutely everything, from the momentum of a moving object, to the incredibly slow decay of radioactive elements, to the bending of objects under forces, to the wobbling of a magnetic particle, all of it emerges from these invisible, complex waves of probability just ticking away in time. It really leaves us with a profound thought, doesn't it? If the very fabric of our solid, everyday reality is built entirely on these strange, ticking, leaking quantum amplitudes, what else might we be completely misunderstanding about the universe? Thank you so much for joining me on this journey into the quantum world. Keep learning, keep questioning, and I'll see you in the next explainer.
Welcome to the Explainer. Today, we're taking the most notoriously weird subject in all of science, quantum mechanics, and we're going to break down its abstract mathematical tools to solve a very real, very tangible molecular mystery. We're going to see firsthand how some seriously heavy math maps perfectly onto physical reality. So let's dive right into the ultimate question. How do we actually predict the future of a quantum particle? Well, to do this, we literally can't use standard physics. We have to build a highly specialized toolkit to figure out how things change at the atomic level over time, step by step, calculating the probabilities as we go. Here's our roadmap for this. 1. The language of quantum states. 2. Defining the base states. 3. The Hamiltonian matrix. 4. The ammonia molecule. And 5. The quantum flip-flop. Okay, section 1, the language of quantum states. Now, you already know that in standard 3D spatial geometry, you can describe an arrow using its x, y, and z components, right? Well, quantum math grounds itself in a very similar way. A quantum state can be described completely by its amplitudes, basically the probability coefficients for its various base states. Because of this incredibly close analogy, quantum states are almost always referred to as state vectors. Let's meet our first mathematical tool, the ket. Proposed by the notoriously quiet physicist Paul Dirac, a ket represents the unfinished half of a calculation. It's an incomplete state vector, just waiting for a partner so we can get a measurable probability out of it. It's really important to remember that on its own, it is not a number yet. And the perfect partner to complete that equation is the bra. When you literally snap a bra and a ket together, you finish the puzzle. You get a bracket, or a bracket equation. This snap is the absolute fundamental action for calculating quantum probabilities. Join them, finish the equation, and boom, your result comes out as an ordinary, measurable number. Moving on to section 2, defining the base states. So how do physicists resolve these state vectors? It's really just 3 logical steps. First, pick a base representation, like a particle's momentum or whether its spin is pointing up or down. Second, assign probability amplitudes for each of those discrete possibilities. And third, mathematically combine them to describe the complete overall quantum state. There's a catch, though. Choosing these base states always requires a few careful approximations. For instance, if we're looking at a hydrogen atom at low everyday energies, we can treat it as a single unit and just ignore its inner motions. But as we look deeper into the universe, particles like protons might have completely unknown internal gears and wheels that we haven't even discovered yet. So defining what we call fundamental base states is entirely tied to the specific energy levels we happen to be dealing with. Section 3, the Hamiltonian matrix. Now that we have our mathematical language and our base states, we need the engine that actually drives change over time. Enter the Hamiltonian matrix, often denoted by the letter H. Think of this as the ultimate energy matrix, the dynamical law for the system. It contains literally all the physics, the forces, the fields, the interactions, the whole shebang. It tells us exactly how a particle's state amplitudes evolve from one moment to the next. If you know the Hamiltonian matrix, you essentially hold the complete playbook for that system's behavior. Section 4. The ammonia molecule. We've got our mathematical toolkit mapped out, so it's time for a test drive on a real physical model. Even the legendary Richard Feynman joyfully pointed out, at long last we have an example of a practical physical problem that you can understand with the quantum mechanics. After all that abstract theory, we can finally apply this math to something undeniably real. Take the ammonia molecule, which has a distinct pyramidal shape. You've got one nitrogen atom and 3 hydrogen atoms forming a base. The crucial point here is that there are 2 perfectly equivalent geometric arrangements. State 1, where the nitrogen is above the hydrogen plane, and state 2, where the nitrogen is below it. Now, to make the math work beautifully, we have to place strict constraints on the molecule. We pretend it has absolutely 0 translational momentum, minimal internal vibration, and that it spins purely on its axis of symmetry. By stripping away all of that extra physical noise, we're left with a highly simplified 2-state system. The nitrogen is either up in state 1, or the nitrogen is down in state 2. And that brings us to section 5, the quantum flip-flop. Here is the big reveal, the bizarre, almost magical behavior of the nitrogen atom inside this molecule. Classically speaking, to get from the up position to the down position, the nitrogen atom would need a massive amount of energy to forcefully push its way straight through the plane of the 3 hydrogen atoms. It simply does not have this energy. No way. But here's the magic of the quantum Hamiltonian. The math dictates a small amplitude that allows the nitrogen to essentially cheat, sneaking straight through that solid energy barrier. This incredible phenomenon is known as quantum tunneling. We can actually visualize this weird tunneling dynamic using a classical analogy you've probably seen in a physics classroom. 2 swinging pendulums connected by a weak spring. If you pull one pendulum back and let it go, eventually the energy transfers completely over to the second pendulum, making it swing, while the first one totally stops. Then the cycle reverses. In our molecule, the probability of the nitrogen being in the up state or the down state sloshes back and forth in that exact same rhythmic way. If we know with absolute certainty that the molecule starts out in state 1 at time 0, our equations prove that the probability slowly dumps into state 2 and then sloshes back again, undulating harmonically over time. The nitrogen is constantly, endlessly flipping states. The math perfectly captures this ongoing probability wave. Which leads us to a pretty tantalizing final thought. If these highly abstract mathematical tools, bras, kets, and Hamiltonian matrices, can perfectly predict the hidden microscopic flip-flop of an ammonia molecule, what other secret inner gears of the universe are just waiting to be unlocked by this exact same math?
Let's just dive right into this explainer, okay? We're going to start at the absolute foundation of quantum mechanics and see how it literally builds a real-world technology. You know, we hear a ton about quantum theory in terms of complex math and these super abstract ideas, right? But it's not just theory on a chalkboard. It actually governs our physical reality in some pretty amazing ways.
So here's the big question for us today. How exactly do you build a machine out of quantum probabilities? I mean, it sounds like a total paradox, doesn't it? But stick with me, because today we're going to explore exactly how these wild abstract equations translate into a physical, working device, a little something called the ammonia maser.
We've got a great roadmap for this explainer. First, we'll look at the ammonia molecule's 2 states. Then, energy in an electric field. Third, we'll actually build the ammonia maser. Fourth, we'll get into the magic of resonance. And finally, we'll wrap up with the absorption of light.
All right, part 1, the ammonia molecule's 2 states. Let's get into it.
Our journey begins with our tiny little protagonist, the ammonia molecule. Think about the physical geometry of what we're dealing with here. Picture a flat plane made of hydrogen atoms, with a single nitrogen atom hovering right above it. But here's the kicker. That nitrogen atom can actually exist on one side of the hydrogen plane, or it can totally flip through to the other side. It's basically acting like a microscopic switch, just popping back and forth between these 2 physical positions.
But if we actually want to build a machine, we have to look past that physical up and down motion of the nitrogen atom. We have to focus on the quantum reality. Because in quantum mechanics, the molecule actually exists in 2 distinct, time-independent states of definite energy. We call these stationary states. So instead of obsessing over where the atom physically is, we have to think about the energy the molecule possesses. Essentially, there's a higher energy state and a lower energy state. Simple as that.
Now, the energy difference between these two quantum states is, well, it's absolutely minuscule. It corresponds to an electromagnetic wave frequency of exactly 24,000 megacycles. To put that into perspective, that frequency doesn't emit visible light at all. It sits perfectly right there in the microwave region.
Moving on to part 2, energy in an electric field. So here is the absolutely crucial point. How do we actually grab onto a molecule this unimaginably small and make it do what we want? Well, the answer is electricity. Because the ammonia molecule has an electric dipole moment, it reacts really strongly to external fields. Just think about how those energy levels behave. Without an electric field, those two energy states are super close together. But the moment we introduce an electric field and start cranking it up, we cause the energy levels of those two states to diverge dramatically. The high energy state gets pushed way up, and the low energy state gets pushed way down.
And you know what? That divergence is our handle. Because the high energy molecules react differently to the electric field than the low energy ones, it means we can finally use physical forces to sort them out. We can literally push the high energy molecules one way and shove the low energy molecules another way.
All right, part 3, building the ammonia maser. Let's build this thing.
Let's jump to the macro scale now and see how all of this builds into an actual physical machine. It's honestly brilliant when you see the sorting in action. Imagine we shoot a beam of ammonia gas out of a little jet, right? And we pass it through an electric field gradient. That's just a field that gets progressively stronger in one direction. Because of that energy split we were just talking about, the high-energy molecules are physically deflected toward the weaker part of the field, while the low-energy molecules get pulled right toward the stronger part. So our single beam literally splits in two, and it does this based entirely on the quantum state of the molecules inside it. How cool is that?
So now we actually have a mechanism for control. Here's how we do it. Step 1, we just discard the low-energy beam completely. We don't want it, toss it out. Step 2, we funnel our perfectly isolated high-energy molecules into a special enclosed space called a resonant cavity. And then step 3, inside that cavity, we gently coax those molecules into dropping down to their lower energy state. And the real magic happens when they drop down, because they have to release all that extra energy.
So putting it all together, we get the complete blueprint of the maser. The beam comes flying in, gets separated by our sorting field, and only that upper trajectory, our VIP high-energy molecules, gets to enter the rectangular cavity at the end. Once inside, that released molecular energy is converted directly into external electromagnetic microradiation. Think about what we're doing here. We are literally powering an electromagnetic field using the internal energy of atoms.
Moving on to part 4, the magic of resonance.
Now you might be wondering, what exactly is happening inside that cavity to force the molecule to drop its energy? Like, why doesn't it just stay happily in the high energy state? Well, the secret ingredient here is resonance. See, the cavity isn't just an empty box. It actually contains a tiny oscillating electric field. And when that field oscillates at the exact, and I mean exact, same frequency as the energy gap between our two ammonia states, which is that 24,000 megacycles we mentioned earlier, it creates resonance.
And the math behind this, it is absolutely beautiful. Under perfect resonance, the probability of the molecule staying in the high energy state falls perfectly and smoothly all the way down to 0. And at the exact same time, the probability of it dropping to the lower state rises perfectly to 1. It's an exact swap. So by carefully timing exactly how long the molecule stays in the cavity, we can practically guarantee it completely gives up its energy to our machine.
And that brings us to part 5, the absorption of light. Now, this beautiful, rhythmic swapping of states isn't just some weird quirk about the ammonia maser. It actually reveals a universal truth about how matter interacts with energy. If the frequency isn't perfectly exact, the transition probability just drops off a cliff. Literally, if you're off by just 4 parts in 100 million, the probability falls to 0. Absolutely nothing happens. And it's exactly this extreme, unforgiving precision that makes these very transitions the basis for hyper-accurate atomic clocks. The quantum rules, they demand absolute perfection.
And if we zoom out even further, this exact mathematical relationship explains how any atomic or molecular system absorbs and emits light. It's wild. If you shine a broad spectrum of light on an atom, that atom will only ever see and interact with the tiny, incredibly specific slice of energy that perfectly matches its own internal resonance peak. Everything else just passes on by.
It all boils down to a really elegant concept.
Basically, the quantum mechanical theory of light absorption and emission is just reduced to calculating these tiny probabilities for specific atomic systems. From a single nitrogen atom just flipping back and forth in an ammonia molecule, we've basically derived the foundational principles that govern masers, lasers, light absorption, the whole shebang. The math tells the atoms what to do, and the atoms physically power our technology.
Which leaves us with a pretty incredible thought to chew on. We literally took a single molecule's tiny invisible flip, and we turned it into the atomic clocks that make our GPS systems work, right? We turned it into the lasers we use every single day. So it really makes you wonder, what other strange probabilistic quantum behaviors are just sitting out there waiting to be harnessed? What invisible mathematical rules are going to build the revolutionary technologies of tomorrow? Something to think about. Keep questioning, keep learning, and I'll catch you on the next explainer. Welcome to this explainer. Today, we're setting the stage for an incredible journey into the elegant, honestly kind of mind-bending mechanics of the quantum world. We're going to look at how nature uses incredibly simple rules to build immense complexity, and we'll be focusing entirely on what physicists call two-state systems.
So, I want you to think about this question for a second. What do the invisible forces holding the center of atoms together, the notorious stability of the benzene molecule, and the bright, vibrant purplish-red color of magenta dye, what do they all have in common? It sounds like a trick question, but I promise you it's not. There is actually a single, surprisingly simple quantum behavior that connects all of these incredibly diverse phenomena.
Okay, let's dive into our roadmap. We'll cover the quantum flip-flop, forces inside the nucleus, the hydrogen molecule dance, solving the benzene mystery, why dyes have color, and finally, the universal spin analogy. Let's get right into it.
Section 1. The quantum flip-flop. Starting with the simplest bond. To really grasp how this works, let's look at the hydrogen molecular ion. We're talking about just two protons and one solitary electron worming its way around them. If the protons are far apart, well, the electron will just stay close to one proton, forming a normal hydrogen atom and leaving that other proton completely bare. That's one state. The second state is the exact opposite. The electron is attached to the other proton instead. Now, classically, it would take a massive amount of energy to rip that electron away. But in quantum mechanics, there is a small probability, or amplitude, for the electron to tunnel through the space between them and jump across that gap. Basically, it exists in a state where it's constantly flip-flopping back and forth between the two protons.
And this brilliantly illustrates what happens to the overall energy of the system. Notice how the energy plummets to a minimum as the distance between the protons decreases. The mere possibility of the electron jumping back and forth actually lowers the total energy of the whole setup. By spreading out, the electron lowers its kinetic energy. And you know what this does? It creates an attractive force pulling the protons together. Chemists call this a one-electron bond. Literally, the flip-flop itself is the glue holding it together.
Section 2. Forces inside the nucleus, scaling up to nucleons.
Now, I want you to ponder something for a second. Could the massive forces binding the nucleus of an atom together actually originate from this exact same flip-flop mechanic? The answer is a resounding yes. If we compare a standard chemical bond with Hideki Yukawa's theory of nuclear forces, we see the exact same pattern. Inside a nucleus, a proton can become a neutron by giving up a particle called a virtual positively charged pion. The adjacent neutron absorbs it, becoming a proton. They are literally flip-flopping their identities by exchanging a pion. The exact same math governing that electron exchange perfectly describes the nuclear force, just at a totally different scale.
Section 3. The hydrogen molecule dance. Adding a second electron.
Let's zoom back out from the atomic nucleus to chemistry. What happens when we add a second electron to our hydrogen setup to create a neutral hydrogen molecule? Now we have electron A and electron B. They're doing this intricate covalent dance, constantly exchanging places with one another. But because electrons are identical Fermi particles, Wolfgang-Pauli's exclusion principle lays down a strict rule. If they're going to occupy this perfectly symmetric, lowest energy bound state, they absolutely must have opposite spins. One spins up, the other spins down. If their spins were parallel, they would actually repel each other.
Section 4. Solving the benzene mystery. A chemical riddle resolved.
All right, we're moving on to a fascinating chemical mystery involving the organic molecule benzene, which is a ring of 6 carbon and 6 hydrogen atoms. Looking at its standard structure, you see these alternating double bonds. Now in chemistry, unsaturated double bonds like these are usually highly reactive. They're really easy to break.
Based on that, you'd calculate a relatively high energy for this arrangement. Yet in reality, the benzene ring is notoriously stable, permanent, and super hard to break apart. Its actual energy is way lower than you'd expect. So why is that?
Well, the solution to the mystery is found right here in its base states. You see, the true ground state of benzene isn't just one static arrangement of bonds, it's a two-state system. The entire group of 30 active electrons is constantly flipping back and forth between two different configurations. There's a specific amplitude that the whole bunch just switches from one dance to the other.
Chemists call this phenomenon quantum mechanical resonance. Because electrons are incredibly light, they find it super easy to flip back and forth. This creates a mixed state, essentially a linear combination of the two base states. And just like with our single hydrogen electron earlier, this rapid flipping causes the overall energy of the molecule to plummet. That massive drop in energy is exactly what gives benzene its incredible permanence and stability.
Section 5. Why dyes have color? The quantum flip-flop you can see.
Let's transition from invisible molecular stability to something we see every single day. How does this quantum flip-flop create vibrant physical colors? Take a look at these two base states for the molecule of the purplish-red dye magenta. It's got a kind of symmetry to it. The molecule features ring structures, and just like benzene, there's an amplitude for all the electrons to flip from one condition to the other. But notice this. The center of electric charge, that little plus sign, shifts dramatically from the right side to the left side as the electrons do their dance. Because of this massive shift in electric charge, the molecule is strongly affected by external electric fields. And what's an external electric field? Light! The rapid flipping creates two stationary states with a specific energy gap between them. For magenta, this energy gap exactly matches the energy of a photon of visible light. The molecule actually absorbs specific wavelengths from white light to power this flip-flop, reflecting back that intense, bright purplish-red color directly into our eyes. It's pretty amazing.
Section 6. The universal spin analogy. The grand unification of two-state systems. We're now going to bring this explanator to its climax by revealing the beautiful underlying mathematical symmetry that unites everything we've explored today. So the crucial point is this: the hydrogen bond, nuclear forces, benzene rings, and magenta dyes are physically totally different from one another, but mathematically, they are identical. Any problem involving a two-state system can be formally translated into the exact same equations that describe a single spinning electron resting in a magnetic field. Literally all of them.
See how this builds into pure geometry. Think about the spin direction of an electron precessing or rotating in a magnetic field. Because of this powerful mathematical analogy, we can solve any two-state problem in the universe by simply tracking a precessing vector as it rotates. You shift your energy zeros, you translate your variables, and suddenly incredibly complex chemistry and nuclear physics just become a geometric problem. It's literally just keeping track of where a vector points after a rotation.
I want to leave you with this provocative thought. How does it change your view of reality to know that a simple geometric rotation explains the fundamental mechanics holding our universe together? I mean, from the bonds in your DNA to the color of your clothes, it all comes down to the elegant, universal quantum flip-flop. Keep seeking, keep focusing, and never lose your curiosity about the structure of our incredible universe.
Welcome to The Explainer. Today, we're diving into what is honestly one of the most mind-bending, astonishing stories in the whole history of physics. We're going to see how sheer abstract math, just the pure raw principles of quantum mechanics, predicted an entirely impossible reality, way before anyone could have even imagined it. Seriously, we're looking at the absolute, astonishing predictive power of quantum mechanics here. So, can a subatomic particle actually change its identity mid-flight? I mean, just imagine throwing a baseball, right? And halfway to home plate, it spontaneously morphs into a tennis ball and then right back into a baseball just before it hits the catcher's mitt. In our everyday macroscopic world, yeah, that sounds like pure magic. There's no way. But down in the subatomic realm, this isn't magic at all. It's a profound, tangible mystery that physicists literally encountered. It all centers around this strange little entity called the K-meson. And to wrap our heads around how such an incredible reality is even possible, we first got to uncover the rules of the matrix it lives in. Which brings us to our first section, the quantum toolkit, or the math of two-state systems. Okay, so before we can solve the mystery of our shape-shifting particle, we need to grab our quantum toolkit. We really need to understand the foundational math of what physicists call two-state systems. Now, you'll see these little mathematical grids. These are known as the Pauli spin matrices. They're named after the physicists who invented them, and honestly, you can think of them as the essential dictionary or really the cheat codes for quantum physicists. If you want to describe a system that can exist in just two states, like say an electron spinning up or down, you don't need infinite crazy complexity. You just need these matrices. They give us the perfect mathematical shorthand to calculate the exact probabilities of a particle being in one state versus another. But alongside our dictionary, we also need an engine, right? Enter the Hamiltonian operator. Now, in quantum mechanics, operators are basically instructions, and you can think of the Hamiltonian as the master instruction set. It corresponds to the total energy of a system. But more importantly for our journey today, the Hamiltonian dictates exactly how a quantum state evolves and changes over time. It's the mathematical driver. It literally tells our two-state system what it needs to do next. Let's move on to Section 2, the polarization puzzle, testing this toolkit on light. So before we tackle those bizarre subatomic particles, let's do a quick warm-up. Let's apply our new toolkit to something we can easily visualize: polarized light. Now, in the classical view, light is just an oscillating wave of electric and magnetic fields. We typically think of its intensity as this smooth, continuous flow of energy. But, as you know, in the quantum reality, light is actually made up of individual, indivisible packets of energy, photons. So when we talk about polarization in a strictly quantum sense, we're treating a single solitary photon as a two-state system. It can be horizontally polarized, or it can be vertically polarized. It can't be like 3/4 of a photon. It's either there or it isn't. It just possesses distinct probabilities of passing through different filters. Picture this. Imagine two sheets of Polaroid filter, offset by a certain angle. Let's call it theta. If a single photon passes through that first filter, it is immediately forced into a very specific polarization state. But when it hits the second filter, what actually happens? Well, classical physics tells us the light wave's energy is just reduced. Quantum mechanics, on the other hand, says that a single photon has a specific probability of passing through, a probability that happens to be exactly the cosine squared of the angle theta. So for example, if the angle is 30 degrees, the photon has a 3 out of 4 chance of making it through. And just like that, we've bridged the abstract math of two-state probabilities right into a physical, highly measurable object. All right, moving into Section 3, Rules of Strange Particles. Enter the K-Mason. Now, when we leave the familiar world of light and step into the bizarre subatomic realm, we find particles that experience what we call strong interactions. Basically, this means when these particles get close enough, they crash into each other and react in massive ways, literally creating and destroying each other in mere fractions of a microsecond. But here's the kicker. When physicists started smashing particles together with high-energy accelerators, they noticed some expected reactions, well, they just weren't happening. To explain this puzzle, physicists Murray Gell-Mann and Kazuhiko Nishijima realized they needed a brand new rule. So they invented a new conservation law and perfectly named it strangeness. Just like electric charge, strangeness must absolutely be conserved in these strong interactions. Ordinary particles like protons and pions have a strangeness of 0. But our K-meson, specifically the K0, has a strangeness of +1, and its antiparticle, the anti-K0, has a strangeness of -1. The fundamental rule is that in any fast, strong collision, the total strangeness before the crash has to equal the total strangeness after. And studying this makes physicists act a lot like detectives. In high-energy events inside a hydrogen bubble chamber, for example, neutral particles like the K0s don't leave any tracks at all. Nothing. But you can clearly see these distinct V-shaped tracks suddenly appearing out of thin air. How? Well, by calculating the momentum and energy of the visible charged particles, the ones that the neutral particles actually decay into, physicists can infer the exact trajectories of those invisible K0s. You can see them indicated by the dashed lines. They literally use that law of strangeness conservation to know exactly which invisible particle was created in the first place. Which brings us to the climax in Section 4, the shape-shifting came on, a glitch in the matrix. Guys, this is where our story takes a genuinely wild turn and reveals a total glitch in the matrix. It all started with a stroke of pure genius by physicists Gell-Mann and Abraham Pais. They noticed a tiny loophole in the rules. See, while strong interactions conserve strangeness, there are also weak interactions. These are much slower particle decays that actually do not conserve strangeness. Because of this, both the K0 and the anti-K0 slowly decay into the exact same thing, 2 pions. Since they share this exact same decay path, Gell-Mann and Pais made this brilliant realization. As the quote says, the K0 and anti-K0 shouldn't be thought of as 2 separate particles at all, but rather as one single interconnected 2-state system. Let's just walk through the exact logic of this identity crisis step by step. Step 1. A K0 decays into two pions with the weak interaction. Okay, simple enough. Step 2. An anti-K0 also decays into those same two pions. Now, because matter and antimatter are symmetric in the specific way, it implies something crazy. There is a mathematical amplitude, a probability, for a K0 to turn into two pions, and then for those very same pions to turn right back into an anti-K0. Yes, you heard that absolutely right. There is a built-in amplitude for a particle to just spontaneously turn into its own antiparticle. And because they can just turn into each other like that, Gelman and Pais went back to the Hamiltonian math, the exact same two-state toolkit we used for our polarized photons earlier, to completely rewrite the equations. They found that the true independent states of the system aren't actually the K0 and the anti-K0. Instead, the pure math dictated two new combined states, which they called K1 and K2. Now, these aren't just clever mathematical tricks. The K1 state decays very quickly, while the K2 state lasts hundreds of times longer. So by representing the particle as a combination of K1 and K2, they effectively set the trap for the ultimate reveal. And wow, here it is, the physical proof of pure quantum logic. Let's say you produce a pure K0 particle in a collision. As it flies through space at nearly the speed of light, the K1 part of its identity decays really quickly, right? But the K2 part, it just keeps on going. Because these two internal states actually interfere with each other, the probability of what the particle actually is changes over time. Just look at this oscillating curve. It shows the chance of finding an anti-K0. It starts at 0 and then smoothly rises and oscillates. You produce one specific particle, and as it simply flies along its path, it literally shapeshifts into a completely different kind of particle, varying its identity over distances of several centimeters. And the craziest part? This was predicted solely by the math of superposition, way before anyone ever saw it actually happen. Which leaves us with this final, genuinely thrilling thought. See, Gelman and Pais, they didn't know the inner machinery of the K-meson. They just trusted the Hamiltonian operator and the fundamental rules of two-state quantum systems. So if pure abstract math can predict an impossible reality, where a particle literally shapeshifts into its own antimatter twin mid-flight, what else is hiding in these equations? What other impossible realities are just waiting out there for us to trust the math enough to go look for them? Thanks so much for joining me on this explainer, and definitely keep questioning the reality around you. Welcome to the explainer. Okay, today we are diving into something absolutely fascinating, the hidden complexities lurking right inside the ground state of a simple hydrogen atom. Now, we're taught pretty early on that hydrogen is the simplest atom in the universe, right? Just one electron, one proton, easy peasy. Most of the time, we just picture its lowest energy level, what we call the ground state, as this single uncomplicated baseline. But when we actually look through the lens of quantum mechanics, the reality is far more intricate, deeply beautiful, and, as you'll see, it actually holds the key to mapping the entire cosmos. So, to really grasp this, we have to ask ourselves a sort of weird question. What actually happens when you put two tiny magnets inside an atom? We usually think of the hydrogen ground state as just a single state. But here's the thing. Both the electron and the proton possess a quantum property called spin. And because they both have spin, they actually generate their own little magnetic moments. So rather than one boring single state, we're really dealing with a four-state system acting exactly like tiny interacting magnets. Notice how the electron and proton spins behave here. They can point either up or down. Because each of the two particles can independently be in one of those two spin directions, boom, we get exactly four possible combinations. These four distinct combinations form the fundamental building blocks, or the univectors if you prefer the math term, for completely describing the quantum state of the hydrogen atom. Now, to keep all this organized without losing our minds, we use a really clean, simple notation. It's pretty straightforward. The first plus or minus sign refers to the electron spin, and the second one refers to the protons. So state 1 with two pluses, that means both are pointing up. State 2 is electron up, proton down, and so on. The cool part is that any state the atom is actually in can be described as a mixture or a linear combination of these four specific base states. But how do these states actually interact and change over time? Well, to figure that out, we construct something called the Hamiltonian operator, which is basically how we calculate the energy of the whole system. Now, because this interaction can't depend on how we happen to orient our coordinates in empty space, it has to be symmetrical. This Hamiltonian calculates the energy based on the dot product of the electron and proton spin matrices, those are the little sigmas you see, multiplied by a constant that we'll just call A. Okay, instead of getting completely bogged down in complex matrix algebra, because who wants to do that, right? We can borrow this brilliant analogy from physicist Richard Feynman. He essentially explains that the math just describes an average interaction energy, which is proportional to the angle between their magnetic moments. Since that electron is constantly buzzing all around the proton, the equation beautifully captures the average magnetic interaction of these two tiny magnets over time. And when we actually take that Hamiltonian equation and solve it for our four base states, we discover something called hyperfine splitting. The interaction of those tiny spins means the ground state doesn't actually have just one single energy level. Instead, the energy levels separate based entirely on how those individual spins interact with one another. So the crucial point here is exactly how that split plays out. The math reveals that three of our mixed spin states kind of group together, and they share a slightly higher energy level of plus A. Meanwhile, that fourth state, it drops way down to an energy of minus 3A. Because of this drop, we end up with a total energy difference between the upper states and the lower state of exactly 4A. Now, you might be thinking, okay, cool math trick. But this energy gap is a physical reality. When a hydrogen atom falls from one of those three upper states down to the lower state, it has to release that exact 4A difference in energy. It literally emits a microwave quantum at this extraordinarily precise frequency, over 1.4 billion cycles per second. And if you convert that frequency into a wavelength, it equals exactly 21 centimeters. Let's zoom out for a second, because this builds into something truly cosmic. Hydrogen is the most abundant element in the universe, so astronomers actually use this exact 21 centimeter frequency as a master key. By tuning radio telescopes to this specific wave, they can locate vast, invisible clouds of atomic hydrogen gas in deep space. They measure the signal's intensity to estimate exactly how much hydrogen is out there, and they even use Doppler frequency shifts of this exact line to map the movement and structure of entire galaxies. It's a real game changer. Up until now, we've seen how the atom behaves in total isolation to create that 21 centimeter wave. But to really understand how atoms absorb or emit these radio waves when we probe them in a lab setting, we have to ask a new question. What happens to this delicate system when it's disturbed by an external magnetic field? To find out, we simply update our Hamiltonian equation. We keep our original spin interaction term, that part stays, but we tack on the individual energies the electron and proton would experience in that new external magnetic field, which is represented by B. We treat them almost as if they were sitting alone in the field, just adding their independent magnetic interactions right into the overall quantum calculation. The result is something known as the Zeeman effect. As we crank up the strength of that external magnetic field along the horizontal axis, check out how our energy lines literally split and curve in different ways. The top and bottom levels change in this straight, linear path, while the middle two levels start out curving before finally straightening out at the higher magnetic field strengths. And the practical consequence of this splitting is actually profound. Because the external magnetic field separates our once grouped energy levels, we no longer get just one single spectral line. Nope. Energy can now be absorbed or emitted across 6 entirely different transitions between these 4 newly separated states. Now, if we zoom way, way in, just looking at very weak magnetic fields, a really fascinating pattern emerges. Notice how that bottom minus 3A energy state stays completely flat. It doesn't change at all, it's totally unbothered. Meanwhile, the upper plus A energy level splits evenly into 3 distinct diverging paths. This visual divergence maps perfectly onto the rules of quantum mechanics. It proves that our 3 upper states group together to act as a spin 1 particle, which inherently has 3 directional base states. Conversely, that lowest energy state, the stubborn one that didn't react to the weak magnetic field, acts entirely as a spin 0 particle. It's this beautiful revelation of how from just 4 mixed states, entirely distinct behavioral identities are born. To truly appreciate the sheer precision of the universe we're decoding here in this explainer, consider this fact. That 14 and 20 megacycle shift we've been talking about is literally one of the most remarkably accurate measurements in all of physics. Like Feynman pointed out, the experimental measurement is so precise that the error margin is only 2 parts in 100 billion. I mean, that is a staggering testament to both the theory and the tools of modern physics. Which brings us to a really fun final thought. We've just seen how the tiny, subtle magnetic interactions of electron and proton spins inside a single, simple hydrogen atom literally allow us to tune in and map the structure of entire galaxies. It's wild, right? It leaves us wondering what other vast cosmic secrets are just hiding right inside the microscopic quantum mechanics of the simplest atoms. Thanks for exploring this with me, and definitely keep your curiosity focused on the incredible microscopic machinery that builds our macroscopic universe.
Welcome to This Explainer. Today, we're diving headfirst into a real quantum detective story. Have you ever actually stopped to think about the absolute, counterintuitive magic happening inside the device you're using right now? I'm talking about everyday technology, like transistors, or even just the basic copper wires hiding in your walls. Well, today, we are going to completely demystify how these materials actually function down at the microscopic atomic level. It is a wildly fascinating journey, and honestly, it flips our everyday intuition totally on its head.
So here's the core mystery we really need to solve. If you look closely at a solid crystal, the atoms are packed incredibly tightly together. I mean, their centers are only a few angstroms apart, and the atoms themselves are about an angstrom wide. If you were to shoot a low-energy electron into this dense, microscopic jungle, you'd probably expect its mean free path to be practically zero, right? You'd think it would bump into an atom almost immediately and just get stopped dead in its tracks. And yet, electrons flow perfectly freely through pristine crystals. So how in the world does an electron survive passing through millions of these tightly packed obstacles without just crashing?
To wrap our heads around this, we kind of have to play Mythbuster with our own brains. Our classic everyday assumption is that an electron behaves like a tiny solid pinball. We naturally imagine it violently colliding with these giant atomic bumpers and just bouncing all over the place. But the quantum reality? It's completely different. The electron doesn't bounce at all. It glides smoothly through the atomic lattice like a wave. It completely bypasses all that pinball chaos. Here is our roadmap for today. We'll kick things off with the conduction mystery, build up a one-dimensional lattice model, and then explore waves and effective mass. After that, we'll expand things into 3 dimensions, discover the weirdness of holes and excitons, and finally look at trapping and bound states.
All right, part 1, the crystal conduction mystery.
Okay, let's dive right in. We are exploring the absolute foundational solid-state physics that makes modern electronics even possible. And the bizarre truth here is that in a perfect crystal lattice, electrons travel smoothly and easily. In fact, they move almost exactly as if they were traveling through a completely empty vacuum. Think about that for a second. In an old-school radio tube, electrons literally move freely through a vacuum. A modern transistor, which is a solid chunk of crystal, is actually able to perfectly imitate that vacuum tube because the crystal lattice allows the electrons to flow just as freely. It is a stunning paradox.
Moving on to part 2, the one-dimensional lattice model.
To understand how a solid chunk of crystal can somehow act like an empty vacuum, we're going to zoom way in and build a mathematical model. Imagine a perfect, evenly spaced line of atoms. Now, most of the electrons in this crystal are tightly bound to their own atoms, stationary and perfectly happy. But we are going to drop one single extra electron into this line of atomic pits. We're going to treat this extra electron almost like a slightly bound negative ion, and we'll track its movement as it jumps from one atom to the next down the line.
Now here is where it gets quantum. When that electron jumps to a neighboring atom, it's not like a physical object leaking through a pipe. It's something physicists call amplitude leakage. And we have to be very careful to distinguish this from basic everyday probability leakage. If you have 2 water tanks connected by a pipe, the water level just slowly and exponentially equals out, right? But quantum mechanics throws an imaginary number, an I, into the math, and that single letter turns that simple exponential draining into an oscillation. Richard Feynman actually had a brilliant way of conceptualizing this. He said amplitude leakage is much more like an infinite row of coupled pendulums. If you start a swing in one, that energy propagates down the entire line as an oscillatory wave.
Which brings us to part 3, waves and effective mass.
Now, what's genuinely fascinating here is what happens when these complex amplitudes actually start oscillating across our chain of atoms. The real part of the amplitude at each atom forms this beautiful, smooth cosine curve. Essentially, the amplitude forms a complex plane wave propagating right along the crystal. The crazy part? The absolute square of this amplitude is mathematically the same everywhere. That means the electron is equally likely to be found at any atom in the chain. It's just the phase of the wave that's changing as it moves down the line.
But, this wave behavior definitely comes with some strict rules.
If you plot the electron's energy against its wave number, which we call k, you'll see that its energy is restricted to a very specific allowed band. It has a strict minimum energy and a strict maximum energy. So if the electron is in a stationary state within this crystal, it is physically impossible for it to possess any energy outside of this specific allowed band.
And here's a fun shortcut. We actually only need to care about a limited range of these wave numbers. If you map out vastly different curves, you'll find places where they intersect the atoms at the exact same spots. The amplitude at every single atom ends up being completely identical. This means any wave number outside our core limited range just mathematically repeats the exact same physical states we've already accounted for. So we can just ignore the duplicates.
Okay, so how do we actually get a moving particle out of all these endless waves? Well, we stack them up. By superimposing several waves with slightly different wave numbers and energies, we create an interference pattern. They cancel each other out in some places and amplify in others, creating a highly localized clump, what we call a wave packet. And because the different waves within it oscillate at slightly different frequencies, this entire clump actually moves forward through the crystal together.
Let's just quickly retrace the logical steps of what we just did, because the equations are about to reveal a stunning coincidence. Step 1. We superimpose quantum waves to make a moving packet. Step 2. We calculate the speed of this packet, which is known as its group velocity. Step 3. When we plug that velocity back into our quantum energy equation, it matches the classical physics formula for kinetic energy perfectly. You know, energy equals 1/2 mass times velocity squared.
So here is the absolute game changer. The complex quantum mechanics of an oscillating electron magically yields a constant that acts exactly like mass. Physicists call it effective mass. As long as we're looking at the gross scale, our weavy quantum packet behaves mathematically exactly like a normal classical pinball particle flowing freely through the crystal. And strangely enough, this effective mass might be completely different from the actual physical mass of an electron in a vacuum. Sometimes it's up to 30 times heavier or even much, much lighter.
All right, part 4, expanding to 3 dimensions.
Now that we've cracked the one-dimensional mystery and see how waves perfectly mimic moving particles, we can expand this into the real world. And the good news is, these principles scale up beautifully to 3D. Instead of just hopping left or right, our electron has an amplitude to leap in the x, y, or z directions. We use a 3D wave vector to track it. But here is the most fascinating quirk. If the crystal isn't perfectly symmetrical, let's say the atomic spacing is wider vertically than it is horizontally, the effective mass actually changes depending on the direction. Yes, an electron localized in a 3D wave packet might have a totally different inertia depending on which way it's traveling. Physicists actually use a complex mathematical tool called an effective mass tensor just to track this directional inertia.
Part 5. Holes and excitons.
Okay, let's make things even weirder and see how this builds into stranger phenomena. What happens when we stop tracking extra electrons and start tracking what's missing? Imagine a crystal of perfectly neutral atoms, and you rip exactly 1 electron out. Now there is an amplitude for a neighboring electron to jump into that newly empty spot. When it does, the empty spot, which we call a hole, effectively moves to the neighbor. Incredibly, the exact same wave equations govern this empty space. The hole gets its own wave packet, its own group velocity, and its own effective mass. It behaves precisely like a real, tangible physical particle moving through the crystal, only it has a positive charge.
Or consider what happens if no electron is missing at all, but one atom simply gets excited by absorbing a photon of energy. That extra energy can literally jump from atom to atom, just like an electron or a hole. The underlying physics remains exactly the same. This moving packet of pure excitation energy is called an exciton. It acts like a moving, neutral particle. And this isn't just some abstract whiteboard theory. Excitons are absolutely vital for real-world biological processes. When light hits your retina, it creates an exciton that travels through the periodic structures of your eye's rod cells to trigger the chemical reaction that literally lets you see.
Finally, part 6, trapping and bound states.
Let's get back to the actual physical crystals inside our phones and computers. Because in reality, what happens when our perfect, infinite lattice inevitably has a flaw or an impurity? Well, there are basically 2 ways this can play out. On one hand, an imperfection could just scatter the wave backward. But on the other hand, if that impurity has a lower energy state than the rest of the band, a bizarre quantum effect called barrier penetration kicks in. The electron gets stuck in what's known as a bound state.
It doesn't just sit perfectly on the impurity, rather its probability of existing kind of leaks out into the surrounding atoms, dropping off exponentially the further away you get. It essentially becomes trapped.
And this right here brings us to a profound universal connection. In high-energy particle physics, there's a fundamental rule. A bound state will exist at the exact energy where the scattering amplitude becomes theoretically infinite, meaning the mathematical principle that dictates how our little electron gets trapped by an impurity in a silicon microchip is the exact same math used to hunt for new subatomic particles.
So, I'll leave you with this incredible, provocative thought. As physicists smash particles together in massive colliders and discover strange new subatomic entities, could some of these new particles simply be combinations of other particles held together in bound states? If so, they are governed by the exact same beautiful, wavy lattice mathematics that allows your transistor to turn on right now. The universe is deeply, deeply interconnected, from the microchip in your pocket to the most fundamental building blocks of reality. Thank you so much for joining me on this explainer, and I really hope this leaves you eager to dig even deeper into these quantum mysteries.
Welcome to this explainer. Today we're diving right in and embarking on a seriously incredible journey, starting from a single subatomic particle and going all the way up to the insanely complex devices that literally power the internet. We're going to explore the physics of semiconductors, the absolute foundation of our entire modern digital world. It is a fascinating story of how just a few clever tweaks to crystal structures gave us the ultimate power to amplify signals, compute data, and basically build the technology that surrounds us every single day. Here's our roadmap for today. We'll start with the semiconductor secret, then meet electrons and holes. After that, we'll look at doping to tailor the crystal, jump inside the p-n junction, explore diodes as one-way streets, and wrap up with transistors as powerful amplifiers. Let's get to it. All right, part 1, the semiconductor secret, cracking the crystal lattice.
To really get this, we need to understand the materials we're working with, like silicon and germanium. They exist in this super fascinating middle ground. And what's brilliant here is that unlike your typical everyday metals, a semiconductor gives us the ultimate control to dictate exactly when and how electricity flows. In their pure form, sitting at absolute zero, these materials crystallize into a diamond lattice structure. Every single electron is perfectly locked into its neighbors. They're complete insulators. But if we introduce a little heat, or as we'll see in a bit, some impurities, we can actually knock those electrons loose. Suddenly, we've got a material whose conductivity we completely control.
Moving on to part 2, meet electrons and holes, the heroes of our journey.
Well, let's meet the two subatomic characters that are going to carry the electricity throughout this whole story. Now, you're definitely familiar with the electron, sure, but its partner? That is where things get truly wild. Check out the origin of our carriers here. Adding energy frees an electron to go wandering through the crystal, but at the exact same time, it leaves behind this positively charged void. We call it a hole, and it behaves exactly like a moving particle. Look at the energy diagrams. It takes a very specific amount of energy, the gap energy, to knock an electron completely out of its bound state. For germanium, that gap is about 0.72 electron volts, and for silicon, it's 1.1. When that electron finally breaks free, it leaves a vacancy. As neighboring electrons hop over to fill that gap, the hole itself effectively moves right through the lattice.
Okay, so you might be thinking, wait a second. It is incredibly counterintuitive to picture a missing electron as a physical, positive entity moving through space, right? So are these positive carriers really a thing, or is this just some math trick physicists use to make the equations easier?
Well, let me introduce you to the Hall effect. This is the ultimate proof. When we apply a magnetic field, the physical buildup of positive charge on the top surface elegantly and definitively proves that these holes actually exist and move independently. Think about it. If you push a current through a block and apply a perpendicular magnetic field, the moving charges are forced upward. If only negative electrons were doing the moving, the top of the block would get a negative charge. But in certain semiconductor setups, the top becomes positively charged. This proves, without a shadow of a doubt, that the primary carriers doing the heavy lifting are acting exactly like physical positive particles.
Which brings us to Section 3, doping, tailoring the crystal and giving our heroes superpowers.
So instead of just waiting around for random thermal energy to knock electrons loose, we can actually alter the crystal lattice to permanently build in these carriers. This is a fascinating process called doping. We engineer the crystal to be totally packed with carriers right out of the gate. Check out the perfect contrast here. Adding arsenic creates an N-type material loaded with extra electrons. But adding aluminum creates a P-type material bursting with extra positive holes. Why? Well, arsenic has 5 valence electrons, When it slots into a 4-valence germanium lattice, it has 1 electron left over. It's bound so loosely that it only takes a tiny fraction of an electron volt to free it, making it a donor of negative carriers. Aluminum, on the flip side, only has 3 valence electrons, so it steals an electron from a nearby germanium atom just to complete its bonds, immediately creating a wandering positive hole. That makes it an acceptor.
Next up, part 4, inside the p-n junction, the dramatic clash.
Okay, this is where our story really heats up. What happens when we take these two highly customized materials and just smash them together? We've got our N-type material loaded with negative electrons and our P-type material loaded with positive holes. When these two regions meet at a sharp boundary, the extra electrons and holes literally diffuse across the gap. They cancel each other out and leave behind this highly charged zone. You'd kind of expect them to just mix together forever, right? But actually, as the electrons wander into the P side, they leave behind positively charged donor atoms. And as the holes wander into the N side, they leave behind negatively charged acceptor atoms.
And because of that, it builds a literal potential hill in the electrical landscape. This means our positive carriers now have to physically climb a steep slope just to get to the other side. Because those stationary charged atoms get left behind right at the boundary, you can see how the electric potential forms a slope. For a positive hole to make the trek from the P side back over to the N side, it has to overcome this built-in voltage barrier. Nature has basically automatically built an internal wall for us.
Part 5. Diodes. One-way streets for directing the traffic.
By playing around with this potential hill, we get our very first major device, the diode. We aren't just observing the crystal anymore, we're actively taking control of the traffic flow. Think of it like a mechanical ratchet. Applying voltage in one direction lowers the hill, letting current flow freely. But reversing the voltage makes the hill way too high to climb, effectively creating a one-way street for electricity. If we connect a battery to apply a forward voltage, we essentially flatten that hill. The carriers just flood right across the junction. But flip that battery around, we add to the barrier. The hill becomes impossibly steep, and the current completely stops dead in its tracks.
This graph beautifully maps out exactly how a small change in forward voltage causes the positive current to increase exponentially as that barrier drops. Just look at the right side of the axis. The very second we push past 0 with the forward voltage, the current skyrockets upward. But on the left side, when we apply a reverse voltage, the current stays practically at 0. This perfectly precise one-way behavior is the absolute bedrock of digital logic.
And now, the grand finale. Section 6, Transistors, our powerful amplifiers.
We have reached the climax of our building blocks Maj. This is where we put two junctions together to create the foundation of all modern electronics. If the diode is a one-way street, the transistor is a fully controllable microscopic dam. Geographically speaking, you can think of the PNP transistor as a three-step journey. Carriers are launched from the emitter, they rush across a microscopically thin base, and then they're swallowed up by the collector. The real trick here is that base. It's unbelievably thin, usually 1/1000th of a centimeter or even less. So when the emitter launches those positive holes into the base, they don't even have time to recombine with the electrons. They just shoot straight across until they hit the steep downward slope of the collector.
Comparing these two landscapes is so cool because you can see how introducing just a tiny voltage to that super thin base dynamically changes the slope of the hill. It instantly opens the floodgates for the main current. On the left, with no applied voltage, the barriers are high and nothing happens. But on the right, as soon as we apply a tiny negative potential to the base, we drop the hill for the emitter. The positive holes just pour right over the edge, skip right through the thin base, and cascade down into the collector.
This is the absolute magic of the transistor right here. By using just a tiny signal to control a massive flow of electricity, we've essentially built a powerful amplifier entirely out of solid crystal. By pulling a microscopic amount of current out of the base, we alter the landscape enough to let a current 100 times larger flow from the emitter to the collector. We've created a valve with literally no moving parts. This one brilliant concept is what allows us to amplify audio, process radio signals, and switch binary ones and zeros at lightning speed.
Understanding exactly how an electron falls down that potential hill is the key to understanding this final question. Think about it. If one single transistor acts as an amplifier, what happens when you cram 50 billion of them onto a piece of silicon the size of your fingernail? It leaves you marveling at the staggering computational power sitting right there in your pocket. Every smartphone, every supercomputer, and the very internet you're using right now to listen to this relies entirely on the precise manipulation of these tiny crystal landscapes.
We've taken this concept and scaled it up to billions of microscopic valves, switching billions of times a second, and every bit of it stems from mastering the magic of semiconductors.
Welcome to this explainer. Okay, today we are diving into what I think is absolutely one of the most fascinating paradoxes in all of quantum mechanics. You see, sometimes, to understand the absolute truth of our universe, scientists literally have to start with a massive, productive lie. Seriously. And this isn't just some quirky math trick reserved for theoretical physicists in a basement. As we'll see, this specific, massive lie is actually the master key. It connects the abstract laws of quantum mechanics to something as real and tangible as the literal color of the leaves growing on the trees right outside your window.
So here's the fundamental problem we're dealing with. How on earth do scientists solve equations that have billions of interacting variables? Just imagine trying to perfectly calculate every single interaction between, say, billions of electrons in a crystal, or the protons and neutrons packed inside an atomic nucleus. These particles are constantly repelling each other, they're spinning, moving, colliding. It is mathematically terrifying. I mean, if you tried to calculate this perfectly from first principles, taking every single tiny repulsion and attraction into account, even our most advanced modern supercomputers would need millennia just to scratch the surface of a fraction of these interactions. It's, for all practical purposes, entirely impossible.
Well, what do physicists actually do when faced with the mathematically impossible? Richard Feynman hit the nail on the head when he said, "We make the most ridiculous approximation that you can think of." We literally use a scientific cheat code, and it's known as the independent particle approximation. In this approach, we basically just pretend that these highly interactive particles don't interact with each other at all. We just ignore the repulsions. We completely ignore the collisions. It sounds totally absurd, right? But here is the truly fascinating part. This lie incredibly unlocks the deepest, most complex secrets of nature.
Section 1. Catching the spin wave. Visualizing the invisible.
Okay, let's dive right into this to see how it builds. Picture a ferromagnet at absolute zero, just a linear array of atoms. Now, in this deeply frozen state, all the electron spins are neatly aligned, pointing strictly up. But what happens if just one single spin gets knocked out of place and flips down? Well, because of the really intense magnetic interaction between adjacent atoms, that flipped spin doesn't just sit there all by itself. The magnetic force compels it to move. There's a super high probability for that downward state to jump to the next atom, and then the next one. It propagates outward, moving exactly like a distinct wave, rippling all the way through the entire one-dimensional lattice. Now that moving wave of downspin behaves remarkably. In fact, it behaves so much like a distinct physical particle, actually possessing its own unique momentum and an effective mass, that physicists decided to give it a name. They call it a magnon. This is what we call a quasi-particle. It's basically a collective, rippling behavior across a solid grid of atoms, yet the math treats it exactly as if it were a real, solitary particle just floating through an empty vacuum.
So what happens if we have a state with two of these downspins bouncing around our lattice at the exact same time? You'd think that, when these two flipped spins get close to each other, reality dictates they should scatter, collide, and interact in highly complex, mathematically exhausting ways. And you'd be right. But to survive the math, we hit our cheat code. We make our ridiculous approximation. We just assume the two waves act completely independently. We calculate the total energy of the system as just the simple sum of their individual energies. We pretend they don't care about each other at all.
And this brings us to a really crucial mathematical distinction about how particles behave under our little approximation here. Magnons behave like identical bosons. This means their mathematical wave function amplitudes add together symmetrically. They are perfectly happy overlapping and occupying the exact same state without any conflicts whatsoever. But if we were talking about extra electrons added to a crystal, those behave as fermions. Governed by the Pauli exclusion principle, fermions are solitary creatures. If you swap two identical fermions mathematically, their wave amplitudes reverse sign entirely. This fundamental rule of reality means two identical fermions can absolutely never occupy the exact same quantum state at the same time.
Moving on to Section 2, the chemistry cheat code, from physics to organic molecules.
You know, this independent particle idea isn't just for theoretical physicists staring at abstract crystals all day. Chemists enthusiastically steal this exact same trick to map out the complex bonds of organic molecules. Take a look at the relatively simple ethylene molecule, which contains just 2 carbon atoms, compared to the much longer and more complex butadiene chain. To understand how electrons behave as we leap from that simple molecule to the complex longer chain, chemists imagine the extra bonding electrons running completely freely across the entire molecular structure.
They purposefully and entirely ignore the fact that these negatively charged electrons fiercely repel each other in reality.
So here is how that actually plays out for the energy of an ethylene molecule. We have two extra electrons making up the bond. Because electrons are fermions, remember our rule from earlier, they absolutely cannot be in the exact same state. However, if one electron has its quantum spin pointing up and the other has its spin pointing down, they're no longer identical in state. Boom, problem solved. Therefore, they can both fall perfectly into this lowest available energy level bucket. By just completely ignoring the repulsion between them, this beautifully simple, independent electron math sets up the fundamental foundation for understanding chemical stability across all molecules.
Section 3. Magic rings and colors. Benzene, butadiene, and leaves.
Let's switch gears a bit and move from linear chains to rings. Starting with the famous benzene molecule. It's a circular structure made up of 6 carbon atoms. Traditionally, you might conceptualize it with 3 separate double bonds, kind of like rigid base states. But if we deploy our cheat code, if we imagine 6 electrons running completely freely around a 6-carbon circular track, totally ignoring their natural repulsion, the math correctly predicts an overall energy state that is fundamentally lower and therefore vastly more stable than those 3 separate static double bonds would ever be.
And the beauty of this math goes even deeper when we look back at the energy levels of the butadiene molecule. Because butadiene is a finite linear chain of 4 carbon atoms. The electrons are confined by the boundaries at the ends of the molecule. When you calculate the allowed quantum states based on those strict boundary conditions, the energy levels map out perfectly onto a geometric semicircle, divided into precise, equal angular slices. It's just a gorgeous, purely geometric way to plot out the normally chaotic world of quantum mechanics.
Okay, now this brings us to an absolutely incredible piece of mind-bending scientific trivia. When you calculate the lowest energy state for butadiene, using those equal angular slices on the semicircle, the math spits out a very specific, undeniable number, 1.618. Yes, the Greek golden mean. The exact same divine ratio found in ancient architecture, the spiraling of galaxy arms, and the arrangement of sunflower seeds mysteriously emerges right here in the foundational quantum math of a common organic molecule. How wild is that?
But wait, this goes way beyond abstract math. Let's ground this firmly in the real world outside your window. Think about a chlorophyll A molecule. It's a massive, intricate structure that features a giant atomic ring where extra electrons are totally free to run laps. By applying this exact independent particle approximation to calculate the allowed energy levels of this ring, we can predict precisely which wavelengths of sunlight the molecule will absorb and which it will reflect. It perfectly explains why plants absorb certain light, and fundamentally, it's the exact reason why leaves are green. The color of nature itself is calculated through a ridiculous physics law.
Section 4. Nature's magic numbers. Filling the energy shells.
All of this brings us to a much broader, truly profound question. Why are certain molecules incredibly stable and durable, while others are highly reactive and volatile? If you think about the smooth curve mapping out molecular energies, pay special attention to the points that dip well below that expected curve. Whenever electrons perfectly fill up an energy shell, which mathematically happens exactly at the ends of these straight-line segments, the entire structure drops to a lower than normal energy state. This creates extreme chemical stability. The molecule is just perfectly content, entirely balanced, and aggressively resists reacting with anything else.
And this theory is so incredibly robust that it beautifully predicts some truly weird and counterintuitive chemistry. Take the triphenylcyclopropanyl cation, for example. The core of this molecule contains a highly stressed 3-atom organic ring. A triangle of carbon atoms is incredibly tense, bent out of shape, and normally wouldn't be stable at all. But our Born approximation accurately predicts that if this tense ring actually loses a negatively charged electron to form a positive ion, it paradoxically perfectly fills a lower energy shell. By losing a piece of itself, this highly stressed ring suddenly becomes exceptionally stable.
All right, now let's zoom all the way past the molecular level, right past the outer electron clouds, straight into the densely packed core of the atomic nucleus. The nucleus is an intensely violent place. It's packed with protons and neutrons where the unimaginably powerful, strong nuclear force constantly battles against fierce electromagnetic repulsion. It's pure chaos. Yet when physicists apply this exact same independent particle math, audaciously pretending the violently colliding protons and neutrons just don't interact at all, it accurately predicted the mysterious nuclear magic numbers. Elements with exactly 2, 8, 20, 28, 50, or 82 protons or neutrons exhibit extraordinary, unexplained stability in the universe.
So the crucial point we're ultimately left with is this. How on earth can such a seemingly ridiculous approximation be the master key to reality?
By purposefully ignoring the chaotic, messy, mathematically impossible interactions between particles, scientists uncovered a brilliant cheat code that allows us to decode literally everything, from magnetism to the color of a leaf. And it really leaves us wondering, how much of the hidden, beautifully structured magic of our universe is only revealed when we actively choose to look at it through the lens of a productive lie?
All right, let's dive right into this explainer. We hear the word quantum tossed around constantly, usually paired with words like weirdness or mystery, but today we're cutting straight through the jargon. We're going to trace a journey from abstract mathematical probability to a highly visual proof of physical reality, showing exactly how moving from a single point on a line to a smeared-out wave inevitably leads us to the discrete energy levels that hold our very atoms together. Here is our roadmap for the explainer. We'll start with the quantum continuum, touch on the uncertainty principle, try pinning down a particle, look at the Schrödinger equation, and finally arrive at quantized energy levels. Okay, section 1, the quantum continuum, moving beyond here or there. So we really have to ask, where exactly is the electron? In classical physics, a particle's location is a total given, right? It's just there. But down at the quantum scale, we've got to throw that out. What if it's anywhere along a continuum? In this realm, we describe the electron using a continuous distribution of probability amplitudes, meaning it actually has a certain likelihood of being everywhere at once. This familiar bell shape, this Gaussian curve, beautifully captures that smear of probability. The very peak? That's your highest likelihood of finding the electron when you measure it. But check out those tails stretching way out on either side. The electron is essentially smeared across space. The width of this curve tells us exactly how localized this probability really is. Moving on to section 2, the uncertainty principle, the strict trade-off of quantum knowledge. Now here's where things get really interesting. The math reveals an inescapable inverse relationship. Position and momentum share the exact same mathematical form. So if you squeeze that wave down, meaning you are super certain about exactly where the electron is, the math literally forces its momentum distribution to spread way out. It's a cosmic game of whack-a-mole. Squeeze one, and you completely lose your grip on the other. And that brings us to the famous quantitative statement of Heisenberg's uncertainty principle. Now, this isn't just because our measuring tools are clunky. No, this is a fundamental law of reality. The product of the uncertainty in momentum and the uncertainty in position can absolutely never be smaller than this specific constant, Planck's constant divided by 4 pi. You simply can't beat that limit. Which leads us to section 3, pinning down a particle, the extreme mathematics of exact location. Okay, but what if we insist on forcing the math? What if we say we know precisely, with zero uncertainty, exactly where that particle is? Well, to do that, we have to pull out a wild theoretical tool, the Dirac delta function. If the electron is dead center at position 0, the probability curve can't have any width at all. It must be 0 everywhere else. But remember, the total probability of finding the electron still has to add up to 100%, or an area of 1. Think about that, a mathematical function that is 0 literally everywhere else, but still somehow holds an area of 1. To picture this, imagine squeezing that Gaussian bell curve to its absolute extreme limit. You make it infinitely narrow and infinitely tall. It becomes this fantastic infinity at one single point that somehow maintains an area of 1. It's some serious mathematical gymnastics just to perfectly localize a particle. All right, section 4, the Schrödinger equation, the master rulebook of probability. So we've got these smeared out probability waves, but what governs them? Enter the Schrödinger equation. Now, don't let the terrifying math intimidate you. It's essentially just a master diffusion equation. Just like a standard equation tells you how heat spreads through a metal bar over time, this dictates how an electron's probability amplitude diffuses. But because it rocks a complex imaginary coefficient, instead of just dissipating like a gas, it curls into these oscillating complex waves. Discovered way back in 1926, this single equation was a massive game changer. It unlocked the secrets of the atom by showing exactly how the curvature of a probability wave interacts with surrounding forces, like the heavy pull of an atomic nucleus. The absolutely crucial thing to grasp here is that this equation links the wave's curvature directly to the particle's energy. The difference between the system's potential energy and the particle's total energy literally dictates how sharply that wave bends. And that sets up section 5 perfectly, Quantized energy levels, the visual climax of bound states. Let's put this all together. Imagine an electron trapped inside a potential well. For this electron to actually be bound inside an atom, its probability wave has to die off to zero outside the well, right? Inside the well, the potential is low. It's nice and cozy for the electron. Outside, it's high. If it's truly trapped, the chance of finding it wandering off at infinity has to be absolute zero. So let's treat this like a quantum Goldilocks scenario. We're going to test different energy levels and see which ones create a wave function that perfectly fits our well without blowing up. Remember, Schrödinger's equation linked energy to curvature, so picking a random energy forces the wave to curve in a very specific way. All we have to do is trace that curve and see if it smoothly flatlines to zero on the outside edges. Okay, test number 1, energy level EA. On the left side, it behaves beautifully, gracefully curving to zero. Inside the well, where the energy is higher than the potential, it naturally oscillates back and forth toward the axis. So far, looking really good. But watch what happens on the right side. The curve suddenly bends upward and shoots off to a massive positive infinity. That means the absolute square, the probability, would also be infinite. The math is basically screaming at us that with this energy, the electron is infinitely more likely to be found completely outside the well. So this state totally fails. The electron isn't actually bound at all. Let's try bumping the energy up just a bit to EB. Well, now the wave overcorrects. It flips right over the axis and plunges straight down toward negative infinity. We changed the energy, which altered the curvature, but we still missed the mark. Once again, the probability blows up to infinity outside the well. Another failed unbounded state. But finally, we hit the just right energy, EC. Look at that. The wave gently approaches zero on both sides, successfully trapping the electron inside the well. Because EC sits perfectly between those first two failed energies, its curvature is tuned to absolute perfection. It doesn't fly up to positive infinity, and it doesn't plunge down to negative infinity. It flatlines precisely to zero. And this right here is the big payoff. This beautifully illustrates our ultimate conclusion. Only a very specific, discrete set of energy levels can ever create perfectly bound waves. And that is literally why energy is quantized. If you shift the energy by even the tiniest fraction, the wave explodes to infinity. The mathematics physically force the electron into these distinct, stacked levels. Now, I know it's easy to get lost in all this math, but we really have to ask, why does this strange dance of discrete waves and potential wells actually matter to you? We've talked about Gaussian smears, delta functions, and wave curvature, but what does a perfectly bound wave actually mean for your everyday life? The mind-blowing takeaway is this. Without this exact quantum machinery forcing atoms into these highly specific energy states, stable matter, including the very cells making up your own body, simply could not exist. If electrons could just hold any random energy, atoms wouldn't have distant structures. They couldn't form the chemical bonds that create DNA, proteins, and literally the entire physical world around us. Quantization isn't just some abstract chalkboard rule. It is the ultimate boundary condition that makes reality possible. And that leaves us with a final thought. If our macroscopic world relies so entirely on the strict mathematical boundaries of the microscopic world, what other invisible quantum rules are quietly holding our universe together? Hello, and welcome to The Explainer. Today, we're setting the stage for a seriously mind-bending journey into the quantum rules that govern our reality. We aren't just looking at what happens in the universe, we're hunting for the hidden architecture of exactly why it happens. Okay, let's dive right into this. Listen to this profound thought from the legendary physicist Richard Feynman. In classical physics, we kind of just accept that things like energy and momentum are conserved, right? But Feynman points out a really beautiful realization. The universe's rules aren't just arbitrary. In quantum mechanics, these conservation laws are actually born from a deeper geometry, from the symmetries of the universe itself. So here's our roadmap for today. We'll trace the origin of conservation, break down symmetry and quantum mechanics, link those two concepts together, and then test it all out on light's hidden angular momentum before tackling the ultimate puzzle, the lambda particle decay. Section 1. The origin of conservation. Classical versus quantum. You know, we're talking about a massive philosophical shift here. Classical mechanics essentially treats conservation laws as practical starting points. It basically says, look, energy is conserved, just accept it, and let's do the math. But quantum mechanics,
it doesn't settle for that. It proves that these conservation laws derive directly from physical symmetries. Quantum physics is absolutely obsessed with uncovering the fundamental why behind the rules. Moving on to Section 2, Symmetry in Quantum Mechanics, the mathematical mirror. To understand that why, we have to define what symmetry actually means down in the quantum realm. Take a hydrogen molecular ion. If we literally reflect the system right down the middle, an operation we call P, we swap the positions of the two identical protons. The state on the left becomes the state on the right, but the physical reality? It remains completely unchanged. That right there is the essence of symmetry. And this brings us to this absolutely beautiful concept called commutation. It's basically Feynman's wait and reflect analogy. If a system is truly symmetric, waiting for time to pass, and then making a reflection, yields the exact same result as making the reflection first and then waiting. When the order doesn't matter, the operators commute. It's like a perfect mathematical puzzle where the sequence of moves doesn't change the final picture at all. You can actually see this timeline in action. If our physical system is fundamentally symmetric, starting with state 1 means it's going to evolve into a specific configuration over time t. Start with state 2, it's perfect mirror image, and it evolves into the exact mirror image of that final configuration. The timeline perfectly reflects itself. All right, Section 3, Linking Symmetry and Conservation. The universe's cheat code. Now, what's really interesting here is that this mapping is practically the cheat code to the universe. It's wild. Every single geometric operation maps directly to a fundamental physical law. If the rules of a system don't change as time passes, energy is conserved. Unchanged from point A to point B, momentum is conserved. Can you rotate it without changing the physics? Angular momentum is conserved. It's pure, elegant magic. Let's look at a very specific operation called an inversion. Imagine taking whatever is at point A and projecting it directly through the origin to the diametrically opposite point, A'. Every single coordinate gets flipped. If a quantum state remains unchanged under this total inversion, it has a conserved property called parity. Definitely keep parity in mind. We're going to need it in a minute. Section 4, Light's hidden angular momentum. Abstract meets physical. We've built an incredible abstract toolkit, so let's pivot to physical reality and test it on something we interact with every single day, a beam of light. These geometric operators manifest in reality when circularly polarized light hits an atom. The rotating electric field of the light literally grabs an electron and drives it in a physical circle, transferring angular momentum directly into the electron itself. Because right circularly polarized light shifts its phase when you rotate it in space, quantum mechanics absolutely demands that it must inherently carry angular momentum. And it does, exactly 1 unit, or +1 h-bar. Our quantum cheat code works perfectly. The math literally just proved that a beam of twisting light physically spins the objects it hits. How cool is that? And finally, Section 5, the lambda particle decay, the ultimate physics puzzle. For our final, most mind-bending application, we're zooming way down into the subatomic world. I want to pose this direct question to you. When this particle explodes, which way will its pieces go? Let's solve a real quantum mystery using the exact rules we just established. All right, here's the setup. We have a lambda particle prepared so its quantum spin is pointing straight up along the z-axis. It's about to undergo a subatomic decay, basically exploding into 2 pieces, a proton, which has a spin of 1/2, and a pion, which has absolutely 0 spin. So, the crucial point here is comparing these 2 possible realities. If the proton shoots upwards, the pion has to shoot downwards to conserve normal momentum. But remember, the original lambda was spinning up. The pion has no spin, so to conserve the universe's total angular momentum, the proton emerging on the top must be spinning up. The path where the proton spins down, completely forbidden by the conservation laws we just learned. And here is the staggering reveal. When physicists actually measure this, the proton prefers to shoot in one direction over the other. The decay is asymmetrical. But wait, if you look at an asymmetrical decay in a mirror, it doesn't match the real world. This means parity is fundamentally broken here. The universe itself actually has a built-in handedness, a literal preference for left over right. We started out with perfect mathematical symmetries, and we end by discovering nature has a flaw, an asymmetry that allows reality as we know it to exist. So it really makes you wonder, what other hidden rules are waiting to be found in the mirror? Welcome to The Explainer.
Today, we're diving headfirst into the bizarre, totally counterintuitive, and absolutely fascinating world of quantum mechanics. We're going to explore how the invisible rules that govern the tiniest particles actually shape our reality, and frankly, how they actively defy human logic. If the quantum realm usually just feels like a chaotic blur of high-level math to you, well, prepare to see it in a completely new, structured light. Let's get started. So let me throw a question at you, one that famously bewildered Albert Einstein himself, prompting him to call it spooky action at a distance. Can measuring a particle right here, let's say in your local laboratory, instantly dictate the physical state of another particle on the exact opposite side of the universe? I mean, human intuition literally screams at us that this is impossible, right? But as you'll see, the universe operates on a very, very different set of rules. Now, to actually wrap our heads around this incredible paradox without getting totally lost in the weeds, we can't just skip to the end. First, we have to learn the fundamental rules of the quantum game. In the atomic realm, there is one immutable law that acts as the ultimate referee for everything. That is the conservation of angular momentum. Literally everything we are about to discuss stems from this single elegant principle. Section 1. The Quantum Spin Rules. Think of the quantum world as having this intensely strict accounting system. Imagine an atom dropping from a high-energy spin state of +1 down to a spin of 0. It has to get rid of that extra angular momentum somewhere, right? So, to balance the books, it emits a right-hand circularly polarized photon, which carries exactly 1 unit of spin away with it. On the flip side, starting from a spin of -1 produces a left-hand circularly polarized photon. The main takeaway? The total spin before and after must always match perfectly. Section 2. Light scattering in action. Classical physics kind of treats light bouncing off an object like a simple ricochet. Just ping, and it bounces off. But in quantum mechanics, the scattering of light is actually a beautifully choreographed two-step dance. First, the incoming photon is completely absorbed by the atom. Then, a fraction of a second later, a brand new photon is re-emitted. So when that incoming photon hits, the atom absorbs it, briefly jumps into an excited spin state, let's say ±1, and then spits out a new scattered photon at an angle. By applying those strict quantum spin rules we just talked about, physicists can flawlessly calculate the scattered light's exact polarization. And the really amazing part? This pure quantum theory arrives at the exact same math that classical physics uses to explain the polarization of the blue sky above us. It all connects. Section 3. The positronium annihilation. Okay, enter positronium. This is a genuinely bizarre, temporary structure that looks a whole lot like a hydrogen atom. But instead of your standard proton and electron, it's made up of an electron and its antimatter twin, a positron. Now, because it is literally made of matter and antimatter, it cannot last. In a tiny fraction of a second, those two particles will inevitably spiral in towards each other and annihilate completely. And right here is where our paradox really starts to take shape. When the spin-0 state of positronium annihilates, the physical particles just disappear, converting their entire rest energy cleanly into 2 photons. To conserve momentum, since the original atom was just sitting there perfectly still, these 2 newly born photons absolutely must fly away in exactly opposite directions. This brilliantly illustrates our core quantum rule in action. Because the initial positronium atom had a total spin of 0, the final state must also have a total spin of exactly 0. It's a non-negotiable rule. Therefore, if one emitted photon is measured as a right-hand circular photon, the other one flying in the exact opposite direction is guaranteed, 100% guaranteed, to also be a right-hand circular photon. Their spins exactly cancel each other out relative to the axis of motion, meaning their quantum states are perfectly inextricably linked from the very moment of their explosive birth. Which brings us to Section 4, Einstein's quantum paradox. All right, here is the absolute crux of the issue. You have a 50-50 chance of detecting a right-hand or left-hand photon on your side of the room. But the very instant you measure your photon and see that it's right-hand circular, you know with absolute certainty what your colleague on the other side of the room is going to measure. It's as if the act of measuring one photon instantly dictates the physical state of the other one, no matter how much distance is between them. Now, this totally shatters our everyday classical assumptions. In our daily lives, we just feel like things have defined independent states before we look at them, right? Actually, scratch that, we don't just feel it. We assume the photon was already right-handed before it even hit the detector. But quantum reality is way weirder. These interacting particles actually exist in a state of interfering amplitudes. Basically, all these possibilities are overlapping one another. It's the act of measurement itself that destroys the interference and forces reality to pick a lane. The legendary physicist Richard Feynman really hit the nail on the head here. He wrote that nature apparently doesn't see the paradox at all. The paradox is only a conflict between reality and your feeling of what reality ought to be. The math perfectly predicts the outcomes every single time. It's only our flawed human desire for particles to act like predictable billiard balls that gets in the way of us understanding what's actually going on.
Finally, Section 5. Measuring invisible nuclear spin.
To prove this isn't all just some abstract philosophical thought experiment, physicists actually went into the lab. They took a carbon-12 target and smashed a beam of accelerated carbon ions right into it. The collision fuses them together, creating this highly unstable, excited state of a neon-20 nucleus. Almost immediately, that neon nucleus decays by spitting out an alpha particle. By placing detectors all around the target, physicists can count the exact angles at which these alpha particles go flying out into the room.
So, remember those quantum rules of angular momentum we talked about earlier? Because physicists know the spin of the carbon and the alpha particles is zero, they can mathematically predict the exact spatial distribution of those final alpha particles. And here is the huge aha moment. When the actual physical laboratory data is plotted out, it maps perfectly onto the theoretical math curves. This is definitive proof showing that this invisible, fleeting neon nucleus has a spin of exactly 1 in one energy state and a spin of 3 in another. It's real, and we can measure it.
We've covered a lot of ground here today. We've gone from the abstract math of angular momentum all the way to the philosophical paradoxes of entangled photons, and finally to a tangible lab experiment mapping the debris of a nuclear collision. Quantum mechanics shows us that the universe follows these strict, beautiful rules that perfectly bridge abstract mathematics and observable reality. But it also proves, without a doubt, that nature simply does not care about our classical assumptions. So I want to leave you with this thought. If these entirely invisible quantum rules so flawlessly shape our physical world, what else is our basic human intuition hiding from us? Keep questioning, keep learning, and thank you for joining me on this explainer.
Welcome to The Explainer. Today, we are diving into something absolutely mind-blowing. We're going to prove that quantum mechanics isn't just some abstract theoretical weirdness confined to dusty chalkboards and massive supercomputers. No, it is the literal, fundamental blueprint of chemistry, of life, and honestly, of every single everyday object you can see and touch right now.
Think about something as simple as a glass of water. If you zoom way, way in and look at a single water molecule, it's actually not arranged in a straight line. It has a very specific, perfectly precise bend of exactly 105 degrees. But why? Why isn't it 90 degrees or 180? Well, the answer isn't just random chance. It literally boils down to a single mathematical formula, Schrödinger's equation.
You know, the brilliant physicist Richard Feynman hit the nail on the head when he said the most dramatic success in the history of the quantum mechanics was the understanding of the periodicities which are found in the table of chemical elements. And that is exactly the journey we're taking today. We're starting from one fundamental mathematical equation and watching how it inevitably builds the entire periodic table and ultimately the whole world around us.
Section 1. The Quantum Blueprint.
To get started, we have to start right on the microscopic ground floor. We're looking at the simplest system in the entire universe, the hydrogen atom. Just one proton, one electron. Okay, so when physicists first tried to pinpoint exactly where the electron in a hydrogen atom actually is, they hit a wall. They realized they couldn't just use standard flat math. To map the electron's potential energy, you actually have to move into a three-dimensional spherical coordinate system, basically tracking the radius from the center and the angles of rotation. We are mapping out real three-dimensional space.
Section 2. Solving the hydrogen atom.
Now, finding the solution to Schrödinger's equation using those 3D coordinates, well, that involves some incredibly grueling calculus. But don't worry, we are absolutely skipping the complex math today. What we really care about is jumping straight to the fascinating physical results. Look at how the traditional 2D mathematical curve showing an exponential wave decay translates perfectly into 3D reality. You get these incredible shapes. The areas with the plus and minus signs are essentially 3D vibrating probability clouds. That's the zone where you're most likely to actually find the electron.
Section 3. Shapes of the electron. Now we have to fundamentally change how we picture an atom.
Electrons are not tiny solid planets orbiting a central sun like a miniature solar system. That's a total myth. They are vibrating, three-dimensional clouds of probability, and they are governed by strict mathematical rules that dictate their exact shape.
The most basic of these shapes is called the est state. In this state, the electron has literally zero orbital angular momentum. Because it doesn't have the energy to spin or orbit around the nucleus in a specific directional way, the resulting probability cloud is perfectly spherically symmetric. So if you're looking for the electron in an S state, you're actually most likely to find it right at the dead center near the proton, with the probability dropping off exponentially as you move outward in a perfect sphere.
And this right here gives us the alphabet of the quantum world. As you add energy and angular momentum to the electron, the math literally dictates that the shapes have to change. Zero angular momentum gives you that single spherical S state, but bump up the angular momentum to 1 and you get the P state, which has 3 distinct directional shapes. Bump it to 2 and you get the D state, which explodes into 5 highly complex lobed shapes. These right here are the real mathematical building blocks of matter.
Section 4, Building the Periodic Table. Okay, let's dive into this and scale up. We've solved the simplest atom, hydrogen, with its single electron. But what happens when we start adding more electrons into the mix to create heavier elements? Well, at first you have these beautiful, simple, evenly spaced energy levels of hydrogen. But as we add more electrons to create heavier atoms, those electrons start repelling each other. Their negatively charged probability clouds actually push against one another. This causes the energy levels to become super messy, overlapping, and skewed. The simple quantum rules suddenly turn into a massive complex juggling act, and that is exactly what makes the periodic table so wonderfully complicated.
But here's the crazy part. Despite all that complexity, the quantum math still forces the electrons to fill up the atom in a very specific step-by-step recipe, which we call the Aufbau principle. Think of it like this. Step 1, you always fill the lowest energy 1s shell first. It holds 2 electrons. Step 2, you move to the next sphere, the 2s shell, filling it with another 2. Step 3, you start filling those directional 2p shapes, which can hold up to 6 electrons. This invisible mathematical recipe is literally the ultimate rulebook for how elements behave.
So the absolutely crucial takeaway here is that this mathematical filling order perfectly predicts chemical reality. Take helium and neon. They have perfectly filled closed quantum shells. Because of that, they require a massive amount of energy, over 20 electron volts, which is huge on an atomic scale, just to rip 1 electron away. As a result, they're noble gases, completely inert. They don't react. But then look at lithium and sodium. The math forces them to have just 1 single loose electron sitting all by itself in a new shell. Their ionization energy plummets to around 5 electron volts. They lose that loose electron super easily, making them highly active, even explosive metals. The math literally dictates the chemistry.
Section 5, The Chemistry of Everything.
Now let's transition out to the macro world. We're going to see how these invisible quantum shapes dictate the physical structures of the molecules that make up you, me, and literally everything around us. Check out this polar graph of an electron in a p state. Notice it's not a sphere anymore. It has these 2 elongated lobes pointing along an axis. Because the electron's probability is stretched out in a very specific direction, it acts exactly like a directional docking station. It can reach out and grab electrons from other atoms, but only along this specific geometric path. This right here is the absolute origin of directed chemical bonds.
Let's compare oxygen and nitrogen to really see this geometry in action. An oxygen atom has 4 electrons in its p state, meaning it has exactly 2 vacancies remaining on its x and y quantum axes. It absolutely needs 2 hydrogen atoms to fill those slots. Nitrogen, on the other hand, has only 3 p-state electrons. That means it has 3 vacant slots across its x, y, and z axes. So it needs exactly 3 hydrogens to complete its puzzle. The math is telling the atoms exactly how many partners they need to bond with. It's like a giant jigsaw puzzle.
Which finally brings us all the way back to our opening question. Why on earth is water bent? Let's ground this abstraction in reality. So, oxygen fills its 2 vacant x and y states with hydrogen electrons. Because of the quantum math we just talked about, those p states sit exactly at right angles to each other, 90 degrees. So initially, the hydrogens lock in at a sharp 90-degree angle. But as they share their electrons with oxygen, the hydrogen atoms are left with a net positive charge. They basically act like 2 positive magnets pushing against each other. This electrical repulsion actually strains those invisible mathematical wave functions, pushing the hydrogens slightly apart, opening that 90-degree angle outward until it settles perfectly at exactly 105 degrees.
And this isn't just some quirky coincidence for water either. Take a look at ammonia, which is made of 1 nitrogen and 3 hydrogens. Because it fills the x, y, and z quantum axes, which all stick out perpendicularly in 3 dimensions, ammonia literally cannot be a flat molecule. It is physically forced by the quantum geometry to form a 3-dimensional pyramid. The invisible math creates the physical shape. No way around it.
So I'll leave you with this final thought. The next time you look at a simple glass of water, are you going to see it the same way? Or will you realize that you are looking at the exact physical manifestation of Schrödinger's quantum equation? From abstract probability clouds to the precise 105-degree bend that literally makes life on Earth possible, the universe is built on a stunningly beautiful mathematical blueprint. Thank you so much for joining me on this explainer. I really hope it sparked your curiosity, and I absolutely cannot wait to explore more of the secret machinery of our universe with you next time.
Welcome to This Explainer. Today, we're going to completely demystify some of the abstract and honestly kind of intimidating math behind quantum mechanics. If you've been following the field, you know that quantum mechanics absolutely loves its abstract algebraic symbols. But today, we're zooming in on a very specific set of tools called operators. Think of operators as the verbs of physics. They're the action words. They're what make the quantum world tick, literally transforming abstract concepts into the physical realities that we can actually measure. Listen to how the legendary Richard Feynman put it: performing an operation on a state produces a new state. Now, in classical physics, we're totally used to straightforward equations, right? You plug a number in, you get another number out, simple. But the quantum universe doesn't really play by those rules. Instead, quantum mechanics uses operations to transform abstract state vectors into entirely new physical conditions. You act on a system, and the system actually responds by changing. Here's our roadmap for today. We'll be hitting 5 main concepts: the quantum translation device, finding the average, position and momentum, the commutation twist, and finally, time and Newton's laws. Let's dive right in. Section 1. The quantum translation device. So, how do we actually do math on a state? Think about it for a second. How do you actually do math on a physical state? In classical mechanics, it was a piece of cake. We just wrote everything in terms of x, y, and z components, or we used neat little geometric vectors with really clear directions. But in quantum mechanics, we use a state vector. And here's the catch. A state vector is not a simple geometric arrow pointing somewhere in 3-dimensional space. It is a completely abstract symbol that stands for a physical situation. So what on earth do we use to manipulate something that abstract? Well, that brings us to our core definition. An operator is an abstract symbol that stands for a physical operation performed on a state vector. So the really crucial takeaway here is that an operator is basically our mathematical translation device. It doesn't work on algebraic functions like your standard derivatives do. It acts on an initial state vector to generate an entirely new one. If you rotate a system or even just wait for a tiny bit of time to pass, you are applying an operator to create a new reality. Moving on to Section 2. Finding the average, predicting the unpredictable. Imagine a system that isn't in a stationary state, meaning it doesn't have one definite energy. If you measure it over and over, you're going to get a completely different result every single time. So, how do you find the average? Well, Feynman uses this brilliant piece of mathematical trickery. The steps involve projecting the state onto definite energy states, figuring out the probabilities of finding each energy, and then cleverly pulling the state vector out as a common factor. The grand finale is operating on the state with something called the Hamiltonian. And just look at the result. Average energy equals the state vector operated on by the Hamiltonian multiplied by the state vector again. This is pure magic. To find the average energy, you literally don't even need to know all the possible energy levels of the system. You just need the wave function and the Hamiltonian matrix. You operate on the state, multiply it by itself, and boom, you've got your expected average. It's an incredibly powerful shortcut. Okay, Section 3, position and momentum, grounding the abstract. If you're looking at a probability density curve for a localized particle, you know the particle is most likely to be found right near the peak of that curve. But where is its absolute average position? Using the operator math we were just talking about, the particle's average position is quite literally the center of gravity of the area under the curve. It's a really neat way to perfectly ground all this abstract math into a visual geometric reality. And this brilliantly shows how we translate back and forth between these worlds. Think of these relationships as our ultimate Rosetta Stone. It translates classic physical properties like energy, position, and momentum straight into their corresponding quantum algebraic operators. Take a look at momentum. To find the average momentum of a wave function, you don't just multiply mass and velocity. You actually have to take the spatial derivative of the wave function and multiply it by Planck's constant over I. And the crazy thing is, this Rosetta Stone applies to even more complex concepts. Take the rotation of axes around the z-axis by a microscopic infinitesimal angle called epsilon. In quantum mechanics, the operator for orbital angular momentum is derived precisely from this concept. You define the angular momentum incredibly smoothly by just seeing how the state's coordinates change when you operate on them with this tiny rotation. Which brings us to section 4, the commutation twist. This is the glitch that literally makes the quantum world happen. Watch how all of this builds into something totally unexpected. In classical physics, if you multiply position, that's x, by momentum, p, and then subtract momentum times position, you get 0. Order doesn't matter, right? 3 times 4 is exactly the same as 4 times 3. But notice the twist when we move to quantum mechanics. The operators for position and momentum do not commute. X times p minus p times x absolutely does not equal 0. It equals I bar, the imaginary unit times Planck's constant. The order of operations fundamentally changes the result. This leads to an absolutely mind-bending realization, captured perfectly by this thought. If Planck's constant were 0, the classical and quantum results would be the same, and there would be no quantum mechanics to learn. That tiny mathematical glitch, that little leftover I-bar you get when you swap position and momentum, is completely responsible for all the wondrous complications of waves, atomic interference, and the entire quantum universe. Without it, our universe would just be a giant, predictable clockwork machine. What's genuinely incredible from a historical perspective is how we even figured this out. Within just a few months of each other in 1926, Heisenberg and Schrödinger independently discovered this exact thing. Schrödinger was over here using differential wave equations, while Heisenberg was working with matrices where order matters, 2 completely different mathematical languages, independently uncovering the exact same fundamental glitch in the universe at the exact same time. Unbelievable. Finally, section 5, time and Newton's laws. Let's bring it back to reality. So, what happens if we use our operators to figure out how the average momentum of a quantum state drifts over time? Well, something remarkable happens. The math spits out exactly Newton's laws of motion. The rate of change of the average momentum perfectly equals the negative derivative of the potential energy. In plain English, force equals mass times acceleration. Deep down in the crazy quantum math, Sir Isaac Newton's classical laws emerge perfectly intact. So, what's the big takeaway here? Operators reveal changes in averages over time, and the drift of the center of gravity for a quantum wave completely matches classical mechanics. It turns out, deep quantum math naturally derives classical force laws. But remember, and this is absolutely key, these predictable laws only apply to the averages, not to the chaotic, detailed internal workings of the atom itself. It brilliantly illustrates that the predictable classical physics we experience every day is actually just the statistical average of underlying quantum behaviors. So, I want to leave you with this thought. The next time you drop a book or watch a ball fly through the air, or even just walk across your living room, ask yourself, are you experiencing absolute classical reality? Or are you just experiencing the massive macroscopic average of a tiny underlying quantum operator dance? Thanks so much for joining me on this explainer, and keep questioning the reality around you. Welcome to the explainer. Today, we're doing something absolutely fascinating. I promise you we're going to skip the heavy calculus. Instead, we're looking at how the deeply weird, microscopic rules of quantum mechanics can actually scale up to create tangible, macroscopic magic right before our very eyes. To set the stage, check out this quote. There are certain situations in which the peculiarities of quantum mechanics can come out in a special way on a large scale. That's from Richard Feynman, and man, it perfectly hooks into our topic today. You know, we so often think of quantum mechanics as this set of rules strictly reserved for invisible subatomic particles. But under the right conditions, those exact same rules govern large-scale phenomena that we can literally hold in our hands and measure. Okay, let's dive into this. Here is our roadmap. Quantum mechanics goes macro, particles and magnetic fields, superconductivity in pairs, the Meissner effect, trapping quantized flux, and finally, the Josephson junction. Section 1. Quantum mechanics goes macro, from invisible atoms to large-scale magic. So, it all starts with temperature.
When you drastically lower the temperature of a system, you're essentially reducing its energy to near absolute zero. At extreme low temperatures, there are very few energy states available. That thermal agitation that normally shakes particles around, it's completely gone, forcing them down into their lowest possible ground state. And when you have an enormous number of particles all locked into that exact same state, their collective quantum nature suddenly becomes visible on a massive macroscopic scale. It's wild.
Moving on to Section 2, Particles in Magnetic Fields, and the quirky rules of the vector potential.
And this brilliantly illustrates a foundational rule. When a particle travels from point A to point B in an external magnetic field, that field actually shifts the phase of the particle's wave function. It modifies the amplitude to take a specific route. And honestly, this shift is the secret sauce to everything that follows.
To really grasp this, we have to contrast two types of momentum. We all know classic MV momentum, mass times velocity, like a physical jolt. But in quantum mechanics, it's a bit different. We use P momentum, or dynamical momentum, which actually factors in the magnetic field. It's this deeper, more abstract P momentum that dictates exactly how the quantum wave behaves.
Now let's think about probability. In quantum mechanics, the probability of finding a particle flows locally, almost like a fluid. Normally, the wave function just gives you the odds of finding a single particle. But what if billions of particles share the exact same state? Well, suddenly it stops being just probability. It becomes the literal physical electric charge density, millions of particles acting as one. Section 3, Superconductivity and Electron Pairs. This is when introverts become a swarm. Okay, so normal electrons are what we call Fermi particles. They are kind of like introverts. They absolutely refuse to occupy the exact same quantum state as one another. But at extremely low temperatures, a tiny, subtle attraction caused by the atomic lattice forces them to bind together into pairs. And once they form a pair, their behavior totally flips. They become Bose particles. Unlike introverts, bosons love to act as a swarm. Every single pair locks perfectly together into the exact same lowest energy state.
So the absolutely crucial point here is that this creates a superconducting fluid. Because these electron pairs are completely locked together in identical states, they move as one massive single quantum river. In a normal flow, you'd knock an electron out of sync, and that causes electrical resistance. But here, you cannot easily knock just one pair out of the flow because of the overwhelming tendency of bosons to stay together. The result is just mind-blowing. Electric current can flow forever with zero resistance.
That brings us to Section 4, the Meissner effect, expelling the magnetic field. Now we get to a phenomenon known as the Meissner effect. If you take a piece of metal, place it in a magnetic field, and then cool it down until it becomes a superconductor, something incredible happens. The metal spontaneously starts up its own supercurrent. This internally generated current perfectly opposes the external magnetic field, effectively pushing it entirely out of its interior.
But the field doesn't just bounce off some invisible shield. It does penetrate just a little bit. We call this the penetration depth. It's an ultra-thin surface layer. To put that into perspective, in a metal like lead, it's about 2 × 10⁻⁶ centimeters thick, literally microscopic. Yet it's within this tiny skin that the protective supercurrents actually flow. The math proves that the external magnetic field dies exponentially the moment it crosses just inside this surface.
Section 5, Trapping Quantized Flux. Magnetic fields in chunks.
Let's move to this next concept and see how this all builds. If you have a normal ring in a magnetic field and you cool it to a superconducting state, it pushes the field out of the metal itself, just like we talked about. But the field still goes through the hole in the center. Here is the really wild part. If you then remove the external magnetic field entirely, those surface supercurrents keep flowing, and the magnetic lines of field become permanently trapped inside the hole of the ring. Now, just imagine tracing a mathematical loop, let's call it path gamma, deep inside the meat of that superconducting ring, where the current is zero. Because the wave function of the entire fluid has to have a single continuous value, when you trace that loop all the way around and come back to the start, the phase of the wave function has to perfectly match up. It must shift by an exact multiple of a full circle. Because of this, the magnetic flux trapped in the hole can't just be any random amount. It is mathematically restricted to exact multiples. And that exact multiple relies on a very specific number, approximately 2 × 10⁻⁷ Gauss square centimeters. Researchers Deaver and Fairbank proved experimentally that magnetic fields aren't smooth when they're trapped this way. They exist strictly in exact, quantized chunks. And, perfectly aligning with the theory, the size of this chunk is driven specifically by the fact that the charge carrying the current is a pair of electrons, not just one. Section 6. The Josephson Junction. The grand finale. Quantum interference of currents. Okay, so here is the setup for a Josephson junction. We have two superconductors separated by a very, very thin layer of insulating material. Now, classically, the current should just stop at the insulator, right? But quantum mechanically, because the barrier is so thin, there is an amplitude for the electron pairs to literally leak or tunnel right across the physical barrier from one superconductor into the other. And this junction has some completely weird, totally counterintuitive properties based on the flip-flop amplitudes of the quantum states on either side. If you apply a standard DC voltage across it, the quantum phase oscillates so fast that no net current flows. But, and this is crazy, if you apply exactly 0 voltage, a current can spontaneously flow. And if you apply an AC voltage, hitting just the right resonance frequencies will actually generate a current. That's a phenomenon known as the Shapiro effect. Now, what's really interesting about this slide is the sheer scale of the quantum magic happening. On the left, we've got a theoretical setup with two Josephson junctions in parallel. On the right, the actual measured wavy oscillatory interference data. Remember the famous double-slit experiment where light creates an interference pattern? Well, this data shows exactly that, but for an electrical current. The wave functions from the two parallel junctions create a literal interference pattern of electrical current, and it's controlled entirely by tweaking the magnetic field between them. Because of these interference patterns, these junctions actually allow us to measure magnetic fields with a precision rivaling the measurement of the wavelength of light itself. It echoes Feynman's absolute awe that we are getting control of nature on an incredibly delicate fundamental level, translating invisible quantum equations into tangible technologies. So I leave you with this. If we can harness quantum magic on a macroscopic scale with this much precision, what mysteries of nature will we unlock next?